Welcome to Cosmic Veil. I spend my life studying the stars, and tonight I invite you to leave the day behind and relax. As an astronomer, my telescope often looks past our familiar sky. Out there, vast galaxies wander through deep space, occasionally colliding in a slow, gentle waltz. Before we open the dome tonight, where are you tuning in from this evening? Whether you are resting in bed, settled on the couch, or outside scanning the night sky like me, I am glad you are here. If these peaceful trips through deep space help you unwind, liking and subscribing truly means a lot. For those who already subscribe, thank you for joining my quiet nights studying the universe. I will try not to keep you awake, but if you and I linger a bit longer in the dark, you will learn a few cosmic secrets. So, as your eyes get heavy, let us look through the lens together. What actually happens when galaxies crash? A collision in space sounds incredibly violent, right? But from my observatory, I track events so massive and slow, they look nothing like a wreck. It is more of a quiet, beautiful dance. Galaxies, huge collections of stars, gas, and cosmic dust, never actually sit completely still. They drift, gravity pulls them along invisible paths, bringing them into graceful encounters that slowly reshape them over billions of years. Tonight, we will observe how these meetings unfold. What happens to the planets swept up in them, and how black holes and dark matter steer the entire breathtaking performance. I will also share my notes on the far future, when our Milky Way finally meets Andromeda, a beautiful union decided by physics long before Earth even existed. Astronomy does not rush anything. Just like the galaxies I observe, we will move slowly, taking time to admire the quiet beauty of the deep sky. Watching these massive cosmic collisions through my lens proves that enormous change can be incredibly gentle and stunningly beautiful. If you could float far beyond our solar system, past the weak light of the stars I chart every single night, you would see the universe is not just random dots. It is built out of massive, glowing cities of light. We call them galaxies, huge structures locked together by gravity. Every single one holds hundreds of billions of suns, moving gas and unseen dark matter that heavily outweighs the things my telescope can detect. These star systems are not just tiny decorations in space. They are the very foundation of our universe, huge islands floating in an endless, dark ocean. To an astronomer, a galaxy is a community. Picture looking down at a huge city from a plane. Every street light down there is a star. Together they build glowing neighborhoods. A galaxy works exactly like that, just on a scale so massive my colleagues and I can barely comprehend it. Take the Milky Way, our home. It is a barred spiral holding anywhere from 200 to 400 billion bright stars. A huge number of those suns host orbiting planets. And on a few of those distant worlds, life might actually exist. Even so, the whole thing spins as one piece, like a giant wheel. You and I might wonder what holds this massive structure together. Gravity, it is the silent builder of the cosmos, the heavy force stopping my favorite stars from scattering into the empty dark. They stay bound because all that weight warps space itself, locking the gas and dust in place. But the bright stuff I photograph, the stars, the glowing clouds, the nebula, is only a fraction of the truth. Dark matter is the hidden skeleton that actually provides most of the heavy lifting. My instruments cannot see it at all, but without its pull, the galaxy would completely fall apart. Everything would spin apart into the dark like untied fireworks. When I catalog galaxies, I see endless shapes, each one shaped by its past. Spirals are the most famous ones. They are beautiful flat disks with arms winding out like giant pinwheels. Those arms are not solid. They are dense waves forcing gas to collapse into brand new stars, creating that bright blue spark I love observing. Our Milky Way fits right in, featuring a thick bar of old stars cutting through the center, if I could view it from outside. Spirals look absolutely stunning, massive swirls of light, like someone sketching across the widest canvas in the sky. Next up are the elliptical galaxies. They are much simpler, just smooth, glowing spheres without any of those flashy spiral arms. Their stars are ancient and cast a soft golden light. My scans show almost no dust left to build anything new. The biggest structures I map out are ellipticals, massive giants that grew over time by crashing into smaller neighbors and absorbing them entirely. They are the quiet elders of deep space, less flashy, sure, but you and I know they hold incredible history. In my studies, irregular galaxies break all our neat rules. I see them as chaotic tangles, born from violent gravity or turbulent histories that destroyed any clear structure. I've found tiny ones and massive ones, but they all share one trait: total unpredictability, while spirals stay neat. These irregulars are cosmic rebels. They remind me that nature rarely follows a perfect diagram. My colleagues and I also group these star cities by size. I observe massive giants holding trillions of suns, and then faint dwarf galaxies with just a few billion. These dwarfs are everywhere. I think of them as quiet cottages next to the towering skyscrapers of spiral galaxies. Even our Milky Way has several small companions, like the large and small Magellanic Clouds, which I've seen from the southern hemisphere as soft, misty smudges. Eventually, our Milky Way will pull these small neighbors in. It shows me that galaxies aren't frozen, they are living actors in a slow, cosmic play. You and I might picture galaxies as quiet paintings, hanging still across the dark heavens. But my telescope reveals constant motion. Billions of stars orbit their centers, gas clouds slowly gather, and glowing arms drift like ripples on a dark pond. When I look up, I don't see a photograph, I see a system evolving over eons. From blazing nurseries where new suns spark to life, to the slow death of ancient giants, I watch the entire stellar life cycle unfold. I read them like ancient libraries. Every glowing star is a page, every cluster a chapter. Yet despite all this wonder, they are incredibly fragile, the beautiful spiral arms I study. The flat disks, they only survive through a perfect balance of gravity, spin, and mass. If that balance shifts even slightly, everything changes form. I've photographed violent collisions. The slow gravity of neighbors can warp these structures, pulling out long tails or drawing strange bridges of starlight. To an astronomer, they seem tough yet delicate. They survive for deep time, but constantly shift and break apart. A century ago, when my predecessors first tracked those faint smudges in the dark, they argued constantly about what they meant. Were they just dust inside our Milky Way, or entirely separate universes floating far away? Back in the early 20th century, Edwin Hubble proved what we now know is true. Those distant smudges were giant galaxies far beyond our own, holding billions of stars. Today, through my massive observatory lenses, I can tell you there are more galaxies up there than grains of sand on Earth. We are looking at trillions of them. Trillions of star cities. Let's think about that together. In all this endless dark, our Milky Way might feel completely normal, but it's truly something special. I map a giant spiral, 100,000 light-years across, turning slowly through the void. Deep in its core sits a supermassive black hole, a silent monster that forces everything to circle. From my backyard telescope, I just see it as a pale, glowing band sweeping across the midnight sky. It always reminds me that we aren't just orbiting one sun. We belong to a massive cosmic community. Honestly, I view galaxies as the universe's neighborhood associations. Only instead of arguing about property lines, they argue over which giant gets to swallow the next tiny dwarf star system. They truly are the social units of deep space. Rarely alone, often clashing, sometimes merging, and always molded by the space around them. Spiral or messy, massive or tiny, I find that every single one has its own pulse, its own story to tell in the cold reaches of space. When I study them, I'm really just trying to understand the enormous stage where the universe performs. They are the silent background and the loud main characters all at once. You can only spot a few with your bare eyes, but my instruments show the real truth. They are everywhere, burning bright all the way to the cosmic horizon. Each one spinning quietly in the cold. Every single one acts as a bright lighthouse against the endless dark. You and I might look up and think space is completely still. The stars seem frozen in their ancient constellations. The Milky Way feels like a solid bridge over our heads, and distant clusters look like frozen, white dust motes. But my data tells a wilder story. Everything is moving. Galaxies drift, spin, and violently crash together, driven by forces I study every single day. To figure out why they act this strange way, I have to look at the two great cosmic sculptors, heavy gravity pulling the strings and invisible dark matter gently guiding the whole dance. Gravity is definitely the most famous force I work with, even though most people completely ignore it on Earth. Really. It just keeps my boots planted in the observatory, and it's the exact reason my late-night coffee mug shatters on the floor when I drop it. For us astronomers, it all started when Isaac Newton wrote the precise math. Proving the force dropping an apple also keeps our moon in orbit and planets circling the sun. Later, Albert Einstein completely changed how we see things with his theory of general relativity. He showed us that gravity isn't just a force pulling things, it is the actual bending of space and time itself. Heavy celestial bodies warp the fabric of reality, and everything just follows those paths. When we observe galaxies, gravity becomes the ultimate cosmic artist. It pulled early cosmic matter into clumps, ignited gas into stars, and sculpted the beautiful spirals and elliptical shapes we photograph today. Without it, we wouldn't have stars, planets, or even us astronomers looking up in wonder. Gravity is the silent director of the cosmic stage, unseen but totally relentless. If the deep space we study is a sculpture garden, gravity is the artist's hand, carving patiently across billions of years. But gravity alone doesn't explain the universe. When my colleagues first studied galaxies up close, we noticed something deeply puzzling. By tracking exactly how stars orbit within a distant galaxy, we calculate the mass needed to hold them together, but our math showed a problem. The visible stars and glowing cosmic gas just weren't nearly enough. Through our lenses, galaxies spun way too fast to be held by visible light alone. Our equations showed they should have ripped apart ages ago. Something huge was missing. We call that missing piece dark matter. Despite how it sounds, it isn't some evil cosmic substance hiding in the deep shadows of space. It just means material that won't emit, absorb, or bounce back light. Basically, it's invisible to our telescopes and cameras, only showing up because of its heavy gravitational pull. Our current astronomical data suggests dark matter makes up roughly 85% of universal mass. It vastly outweighs every star, planet, and galaxy we observe. Picture a galaxy as a bright lantern trapped inside a massive, completely invisible balloon. The lantern is the glowing dust, while the balloon is dark matter locking everything tight. Without this hidden structure, the galaxies we map simply wouldn't exist. They'd just be chaotic swarms of stars, losing their beautiful spiral shapes entirely. Dark matter is the universe's quiet scaffolding, stopping the bright structures we study from scattering. It's still a deep cosmic mystery, but we know what it isn't. It isn't built from the normal atoms making up you, me, or the observatory floor. It's not just regular dust hidden in dark clouds or dim stars. Decades of scanning the sky ruled that out. Instead, our data points to something totally different, a strange particle that completely ignores light. My colleagues worldwide are burying ultra-sensitive astrophysics detectors deep underground, hoping to catch a tiny whisper of dark matter drifting by. We haven't caught it yet, but its gravitational fingerprints cover the night sky. Gravity and dark matter join forces to build the grand architecture of space. They never work alone. They actually weave the cosmic web together. We see galaxies gathering along massive dark matter threads, building huge astronomical superclusters. Between them sit immense empty voids. Dark regions almost completely empty. This massive cosmic structure basically resembles a glowing three-dimensional spiderweb spanning billions of light years. If you and I could step outside the universe to look, we'd see brilliant galaxy threads tracing that invisible dark matter scaffolding, pulled incredibly tight by gravity. So why do these galaxies move? If gravity holds them so tightly, shouldn't they just stay frozen in neat little patterns? The truth is, galaxies are born already moving. Right after the Big Bang, tiny density ripples gave certain patches a head start in grabbing mass. As those regions expanded, their pull dragged more material inward, not in straight paths, but along curved ones that gave galaxies a natural spin and drift right from birth. Today, we watch galaxies tugging at their cosmic neighbors. Our own Milky Way isn't just floating lazily in the dark. It's racing toward Andromeda at hundreds of thousands of miles an hour. Thankfully, deep space is massive, so that huge collision won't hit us for another 4 billion years. For you and me, that feels like eternity, but on my astronomical calendar, it's right around the corner. The takeaway is that galaxies aren't lonely marbles. They're locked in a giant gravitational dance, every step driven by their partners. And watching these galaxies interact is one of the most beautiful sights through my telescope. Through my telescope, I see some just brush past one another, stretching their shapes with tidal forces. Others embrace completely, melting into new galactic forms. Gravity directs these cosmic dances, tugging at the edges of star systems long before their cores meet. Stars get pulled into long, glowing tails. Vast gas clouds compress to ignite fresh stellar nurseries, and massive central black holes might finally spiral together. What looks like pure chaos to us is actually physics unfolding perfectly across distances we can barely imagine. I am always struck by how endlessly patient gravity remains. You and I usually think of crashes as sudden, violent, destructive things that end in a fraction of a second. But out here in the cosmos, a collision is just two clouds drifting together, a slow, gentle drift spanning hundreds of millions of years. The physical forces are massive, but the rhythm is incredibly calm. Gravity operates on a schedule so grand that entire stars are born and die while these galaxies slowly combine. Invisible dark matter also plays a huge part in these cosmic meetings, when two galaxies crash together. Their shining stars might warp wildly, but their dark matter halos pass right through each other like two unseen balloons. These unseen shells are far bigger than the star clusters themselves, silently steering the entire merger to shape the final, beautiful form. Watching these slow collisions gives astronomers like me our greatest tool to trace where all that hidden dark mass actually lives. Looking at all of this, a deep truth emerges. Space is never still. It is no quiet museum of frozen exhibits, but a breathing, shifting web of galaxies, carved by forces both seen and unseen. Gravity softly bends the paths. Dark matter builds the framework. Together, they set the stage for beauty on an epic scale. When I study a galaxy, I see a delicate balance between the physics we grasp and the mysteries we chase. It feels like witnessing the slow, patient art of the cosmos. A grand design carved not into rock, but in starlight. Understanding these pulls and pushes tells us more than just why distant spiral galaxies take their shape. It reveals why space has any structure at all. Without gravity's pull, loose matter would never have clumped into bright stars. Without dark matter anchoring things down, galaxies would fly apart before their stars could forge planets or give life a chance to spark. Every single breath, thought, and dream owes its existence to these quiet cosmic architects. Deep space is vast, but its story is driven by a very small cast of characters, each playing parts as old as time itself. Through a backyard telescope, galaxies look like painted ornaments in the dark, but they are never truly still. They are ancient drifters, changing and reshaping across eras so huge that a star's entire lifespan feels like a brief blink in comparison. Let us step away from human time for a moment. You and I must enter space where billions of years simply unfold like chapters in a long, unhurried book. Every single galaxy begins as a simple gathering of matter in the infant universe. Right after the Big Bang, roughly 13.8 billion years ago. Space was mostly a smooth soup of hydrogen and helium gas, but hidden in that vast, even ocean were tiny ripples, little changes in density, so small I might have missed them completely. Across massive, stretching eras of time, gravity boosted those tiny waves, dragging extra cosmic dust into the slightly heavier pockets. What started out as a barely noticeable shift finally grew into the very first star clusters of the ancient galaxies. Those early star systems were small, messy, and totally irregular. When I look back at them, I see only brilliant young stars because the cosmos was too new for anything to grow old. Free gas was everywhere, sparking massive bursts of star birth. Placed next to the grand spirals and huge ellipticals we observe tonight, those early galaxies were just tiny seeds pushing up from the dirt. They lacked beautiful symmetry, but they held the raw ingredients for massive cosmic growth. Over billions of years, galaxies changed through deep inner mechanics and violent outside meetings. Inside the core, stars ignited, lived out their bright lifespans. and died, flooding the empty space with heavier atomic materials like carbon. Oxygen and heavy iron, those exact elements allowed rocky planets to form around warming suns, eventually letting life spark in at least one quiet corner of the sky. Every fading star generation left a permanent fingerprint on the galaxy's true nature, slowly shifting its hue from a harsh, youthful blue to a soft, golden glow as the frantic star birth finally slowed down. From the outside, neighboring galaxies constantly tugged and reshaped each other. Space was much tighter back then, making galaxy collisions far more common than they are tonight. These meetings were never quick accidents, but massive, slow-motion events dragging on for hundreds of millions of years. When entire galaxies hit, the actual stars usually slipped past each other without touching. After all, a single star is incredibly tiny compared to the black voids between them. Yet you and I watch their structures change forever. Massive gas clouds crash together, sparking brilliant new waves of star birth. I watch spiral arms stretch into massive tidal tails, as two colliding galaxies slowly merge into one giant system. People often ask me if these collisions are purely destructive. The truth is, they are beautifully creative. Without these mergers, the massive galaxies we observe tonight simply would never have formed. Those giant elliptical galaxies anchored at the center of star clusters, I see them as products of countless mergers over billions of years. It is a record of cosmic cannibalism, written entirely in starlight. Even our own elegant Milky Way will not last forever. In my research, I see past collisions that left faint streams of stars arcing across our galactic halo. And its future definitely holds a grand collision with Andromeda. This endless life cycle shows us just how incredibly dynamic these structures are. A spiral galaxy might eventually run out of gas, slowing down its birth of new stars. It fades into a quiet red glow. Over billions of years, steady mergers erase those delicate arms, leaving me to observe a smooth, rounded shape. By that time, most of its stars have grown old. They glow faintly, burning the very last of their nuclear fuel. The galaxy itself remains vast and bright, but it begins to sleep. A once busy cosmic city fading into a calm twilight. Honestly, timelines like this stretch even my own imagination. Let us take a moment together. Saying a collision takes hundreds of millions of years is easy, but actually grasping it is hard. Consider this: the entire run of human history, from early farming villages to modern skyscrapers, spans just a few thousand years. Even the complete age of the dinosaurs lasted only a few 100 million years. That is barely a single chapter in a galaxy. These star systems never hurry. I watch them shift at a pace so slow. Entire species and planets rise and fall without the galaxy changing its look at all. Yet I find a deep comfort in this endless space. Knowing these star cities survive for billions of years proves our universe is incredibly patient, giving every cosmic cycle the time it truly needs. Collisions, mergers. The birth of new suns are not violent mistakes, but the natural rhythm of space. Through my lens, galaxies are never fragile like a single planet might be. They are tough, massive groups that easily survive impacts that would utterly destroy a smaller world. Even our own Milky Way carries scars from its past. My colleagues and I have traced ancient star streams from tiny dwarf galaxies, completely swallowed up by our own. When I map these faint sky trails, I am reminded that star systems never live alone. They constantly brush against each other. Every single merger adds a new chapter, slowly shifting its shape, bringing in fresh star clusters and driving its slow, steady growth over time. Certain galaxies live very quiet lives, drifting alone in the dark. Others pack into dense clusters where collisions happen often, speeding up their evolution. The wild variety of shapes I photographed tonight is just a brief snapshot of their long journey. A spinning spiral might someday settle into a blank oval. A messy gas cloud might finally take a solid shape. I see the universe constantly sculpting these massive structures using nothing but gravity and time. When you and I look up at these ancient giants, our entire view of the world just shifts. Our daily worries of hours and days feel so incredibly small against the silent drift of a billion stars moving across the deep void. Yet rather than making me feel small, I find this massive scale incredibly soothing. It reminds me that this universe is wide enough to hold absolutely every story. From our brief human spark to the slow turning of a spiral galaxy, each runs on its own clock, equally important, all bound together in the deep fabric of space. Whenever I peer through the observatory glass, or even just picture it, I am watching time stretch far beyond what my mind can handle. That starlight has crossed millions of light years just to hit my lens, bringing an ancient record of the deep past. Meanwhile, the system itself simply continues, changing in ways I can only catch a fleeting glimpse of tonight, because to an astronomer, galaxies are never just groups of random stars. They are cosmic history books, living monuments to the slow and quiet patience of deep space. When people ask me about colliding galaxies, their imagination usually jumps straight to chaos. You might picture giant suns smashing together, planets flung into the dark, and massive explosions tearing the sky apart. It sounds exactly like a loud summer action movie. Fast, burning, and completely destructive, but through my telescope, reality paints a very different picture. Stick with me here, the math shows us a slow, beautiful transformation. It is not an act of destruction at all, but a graceful ballet moving on an endless scale. The biggest secret of astrophysics is that stars almost never actually hit each other during these massive mergers. I know that sounds completely backwards. Every galaxy we study holds hundreds of billions of burning stars. You and I might think two overlapping galaxies would smash together like cars in traffic, but the secret to this lies in cosmic scale. Stars might dwarf our planets, but they are incredibly tiny compared to the deep, empty space between them. Picture two single grains of sand resting several miles apart. That is roughly the distance between stars in any given galaxy. Even when we watch two galaxies drift through each other, the odds of stars actually crashing are near zero. The reality is far softer. The immense gravity of each galaxy gently pulls on the other, warping their beautiful shapes. These gravitational tides stretch them into long, elegant tails of starlight, beautiful arcs that sweep across hundreds of thousands of light years. However, giant gas clouds do crash and squeeze together. As astronomers, we know these deep space clouds are where the real fireworks happen. The heavy gas collapses under gravity, sparking massive bursts of new stars. These massive encounters rarely destroy stars. Instead, they give birth to new ones, lighting up the deep sky in a fresh blaze of bright fire. For those of us watching, this rapid starburst is the most stunning part of a collision. As the gas squeezes tight, it forms glowing cosmic nurseries filled with massive, boiling stars. They burn bright but die young, ending in massive supernovas. These blasts scatter heavy, rich elements out into the dark space around them. Because of this, these cosmic crashes add more than just beauty to the night sky. They create the very chemistry of space. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all forged in the fires of ancient, dying stars. Galactic mergers speed up this grand cycle, feeding the universe fresh material for planets and life. Another fascinating thing we observe is how these events rewrite stellar motion. While stars miss each other, shifting gravity completely alters their long, quiet orbits. A few lonely stars might get thrown into sweeping arcs around the newly merged galaxy. Others slowly drift toward the galactic core. We even calculate that entire solar systems can be gently pushed, sailing calmly from one edge to another. If you stood on a distant planet orbiting its sun, the dark sky would shift over time, familiar constellations slowly unraveling as the galaxy reshapes. But for anyone living there, this cosmic ballet moves so slowly, they would never see a single change during their entire life. Let's clear up a common myth together. People think these collisions are violent, explosive events that destroy everything, but the truth is incredibly calm. These massive galaxies drift through each other like ghosts, leaving stars completely untouched. Their gas clouds spark new life instead of ending it. For us stargazers, it proves that a word like collision is totally wrong for the deep, quiet void of space. We don't call them crashes, they are slow mergers, silent dances, and beautiful transformations. When we watch two similar-sized galaxies finally blend, they usually form a completely new type of galaxy. Beautiful spiral arms are pulled apart, fading into a softer, much rounder elliptical shape. Across billions of years, that messy aftermath calms into a quiet, stable structure. The ancient stars drift peacefully along their brand new paths. Through our lenses, the galaxy looks smoother, much simpler than a spiral, but it hides the deep, structural memory of those ancient cosmic unions. Because of this, every elliptical galaxy we catalog is a silent monument to ancient mergers. Think of them as cosmic scars healed into something beautiful. Sometimes, though, we observe an unequal match. A massive giant simply absorbs a much smaller companion. In my field, we playfully call this galactic cannibalism, but it is hardly a bloodbath. The little galaxy is gently pulled apart. Its glowing gas and stars slowly melt right into the giant. We look for proof of this in faint stellar streams circling many large galaxies. They are the ghostly leftovers of dwarf systems swallowed a long time ago. Even right now, our home, the Milky Way, is actively eating its smaller galactic neighbors. Their remains orbit us as pale, ghostly trails across the dark sky. We've learned that gas dynamics actually run the show during these encounters. Unlike individual stars, thick gas clouds are big enough to smash directly. When they hit, massive shock waves ripple through the darkness. The gas loses its energy and slowly sinks down toward the galactic core. This falling gas feeds the supermassive black holes hiding in the center. Suddenly, they flare up into violently bright active galactic nuclei. These brilliant beacons shine brighter than the entire host galaxy. They are fueled by pure matter spinning down into the black hole at near light speed. This is how mergers awaken sleeping black holes, turning quiet galaxies into blinding quasars we can spot from Earth. For you and me, the pace of this is almost impossible to grasp. A deep space collision simply doesn't happen overnight. Just the initial approach takes hundreds of millions of years. Then begins a very long, quiet dance of close passes, slow drifts, and eventual returns. Only after tracking them for perhaps 1 billion years will we see these beautiful giants finally become one. To put that in perspective, you and I should consider that 1 billion years is roughly how long simple life on Earth took to become complex. As we watch galaxies slowly weave together, entire worlds can rise, thrive, and fade away without ever witnessing the full cosmic event. For astronomers like myself, studying galactic collisions acts as both a window into deep history and a forecast for tomorrow. By observing star systems in different merging stages, we can actually piece together the entire life cycle of these grand encounters. I often study the antennae galaxies, 2 spiral systems currently caught in the heavy throes of collision. Their long tidal tails arc outward, resembling glowing insect feelers. In my observations, the Whirlpool Galaxy shows a smaller companion disturbing its delicate structure, gently tugging its spiral arms. Every cosmic example we map is merely a snapshot of an ongoing story, a frozen frame in a movie playing out over eons. In tracking these collisions, I have really come to appreciate the profound role of patience in our universe. To human eyes, they look catastrophic, yet on cosmic timescales, I assure you they are neither sudden nor ruinous. Instead, I view them as natural steps in galactic evolution, absolutely essential for growth. Renewal and deep change. If galaxies could speak to us, they would not call these encounters disasters, but rather beautiful transformations into something entirely new. In the very end, our science of galactic collisions proves that appearances can be deceiving. What looks like pure destruction is often just creation in disguise. The individual stars carry on undisturbed. Gas ignites with fresh energy, and entirely new galaxies slowly emerge from the union. Instead of picturing fiery wrecks in deep space, I prefer to imagine a very slow dance. A gentle blending guided by gravity, lit by the birth of countless new suns. Through my lens, it is not a vision of violence, but of cosmic renewal, written across billions of years in the calm starlight. When 2 massive galaxies meet, the result is not just a messy rearrangement of stars and gas, but a display of breathtaking cosmic artistry. These encounters build structures so striking that even seasoned astronomers like myself are left completely in awe. Long tails of starlight unfurl into the dark. Bridges of matter stretch between galaxies like warm, glowing handshakes. Let's look closely at these delicate streams arcing across space, resembling brush strokes on a canvas larger than we can imagine. It is exactly why I describe galactic collisions as ballets. They are graceful, deliberate, and hauntingly beautiful. One of the most captivating features my colleagues and I study are tidal tails. These elongated streams of stars and gas extend from colliding galaxies, stretching for hundreds of thousands of light years. I watch them form as the immense gravitational pull of one galaxy heavily distorts another, tugging at its outskirts and flinging stellar material outward in elegant arcs. Through an eyepiece, tidal tails look like ribbons of light drifting into the void, their smooth curves perfectly echoing the flow of gravity itself. We see some tails eventually curl back, falling right into the merger, while others remain as faint reminders of past interactions, lingering for billions of years. Bridges are another common feature I map in galactic interactions. These glowing connections form when star material is drawn from one galaxy to another, creating a luminous thread right between them. To my eye, these bridges resemble shimmering trails of starlight linking two lonely islands in the dark ocean of space. They are the visible, glowing evidence of gravitational attraction at work, a grand cosmic tug-of-war in stars and gas. Over time, I watch such bridges collapse back into their host galaxies, but while they exist, they give the vivid impression of galaxies reaching out, almost touching. Stellar streams also result from these collisions, forming when massive galaxies tear their smaller companions completely apart. I track these streams. They are often faint but remarkably long, wrapping around galaxies like glowing halos or forming graceful loops. Right here in our Milky Way, we have detected such streams as remnants of dwarf galaxies consumed long ago. They serve as the lingering choreography of past dances. Subtle, elegant signatures of the ancient encounters that shape the galaxy we live in today. The sheer beauty of these cosmic structures amplifies when I use telescopes capable of capturing both visible and completely invisible light. My ultraviolet observations reveal brilliant bursts of new stars forming within the tidal tails, while our infrared views show glowing dust heated by young stellar nurseries. Using radio telescopes, I pick up hydrogen gas stretched across vast distances, mapping the invisible currents feeding fresh star formation. Taken together, these perspectives show me that collisions are not chaotic events, but beautifully ordered compositions. Each specific wavelength of light adds another distinct note to our cosmic symphony. So, while we observe these galaxies mid-performance, let's use computer simulations to replay their entire choreography, with the help of modern computing power. In our labs, we model galaxies using millions of tiny particles. Each represents stars, gas, or dark matter. When we set two simulated galaxies on a collision course, the results look astonishingly real. Spirals twist, tails unfurl, and starry bridges appear exactly how we see them through our telescopes. Our cosmic models are not just scientifically useful, but mesmerizing. They let us watch billions of years unfold in mere seconds. What makes these computer simulations so striking is how they reveal the deep rhythm of the cosmos. These star systems sway and stretch, not with violence, but with a gentle grace dictated by gravity. They approach, overlap, recoil, and return, moving like two dancers sharing a cosmic duet. Eventually, they merge into one massive form. The chaos gently gives way to deep calm. The pace feels slow, yet the patterns show us how simple gravitational forces create stunning beauty on scales we can barely comprehend. When you and I study these deep space collisions through our observatory lenses, the imagery strongly resembles beautiful earthly art. The glowing arcs of tidal tails resemble soft brush strokes from an unseen hand. Looping star streams mimic giant calligraphy written across the night sky. Their delicate bridges could be mistaken for a graceful ballet dancer frozen in motion. I know there is no intention behind these displays, no audience they were created for. Yet as an astronomer, they stir in me the exact same response as fine art, a quiet, deep wonder. The calm pace of this stellar dance is part of its beauty. Unlike the violent crashes we expect on Earth, these giant galaxies move with unhurried grace. Their slow encounters last for hundreds of millions of years, each single step stretching out far longer than all of human history. When we watch from our distant vantage point, the whole spectacle feels totally serene. even during their most dramatic cosmic encounters. These galaxies move with a patience reflecting deep cosmic time. Just look at the antenna galaxies, one of our favorite examples of a beautiful galactic collision. From our telescopes on Earth, they look like two spirals locked in an embrace. Their cores glow brightly, while long stellar tails sweep out like curved antennas. Deep inside those sweeping tails, young stars sparkle in clusters born from heavy compressed gas. The whole system pulses with raw energy, yet to my eye, the arrangement is perfectly elegant. The antenna galaxies remind us that even during massive upheaval, our universe creates forms that completely captivate us. Another striking object we study is the Cartwheel Galaxy. Its unusual ring shape formed when a smaller galaxy punched right through a larger star disk. That massive impact sent ripples outward through the gas, much like tossing a heavy stone into a pond, creates perfectly expanding circles. Those ripples triggered massive waves of star formation, forging the glowing outer ring that gives this strange galaxy its famous name. For us as scientists, the Cartwheel perfectly demonstrates how these slow impacts reorganize matter on a truly colossal scale. But just looking at it, the shape seems almost too perfect. Like a deliberate design etched against the black void, what always strikes me as an astronomer is their total impermanence. Those glowing tails eventually fade away, star bridges collapse, and stellar streams just disperse into halos. The beautiful shapes we map are just fleeting chapters in a galaxy's life, visible to our cameras for a few 100 million years before fading. On a cosmic scale, that is incredibly brief, just a passing flourish in a deep space performance spanning eternity. You and I are lucky to witness them at all. Honestly, it feels like a rare cosmic gift. A gentle reminder that beauty can emerge at any scale, even if only for a little while. My favorite way to picture these deep space events is as a giant cosmic dance floor, where distant galaxies glide past in endless waltzes. We track no sudden movements, no rushed steps out there, only the steady pull of gravity guiding their motion. Each galaxy bends and sways, trailing huge ribbons of starlight sweeping through the deep dark. Through my eyepiece, the sight is totally tranquil, deeply meditative. It is a silent performance that easily lulls the mind into peace, as if the universe itself were slowly choreographing a beautiful lullaby. This galactic ballet is a brilliant testament to the sheer power of perspective. Up close, our data shows immense turbulence, violent shocks, and chaotic starbursts. But viewed from millions of light years away, sweeping curves reveal pure grace. It proves to us how the exact same event can be intensely disruptive, yet endlessly beautiful, depending entirely on the scale of your lens. For us astronomers, that duality is where the true fascination lies. They remind you and me that space is not just cold mechanics. It is a canvas where hard physics writes poetry right across the stars. Across the visible universe, countless galaxies have collided, merged, and completely reshaped themselves. But a few specific systems have become true icons in our field. They are our true showpieces, the galactic celebrity couples that draw every eye whenever we release a brand new telescope portrait. Look up with me tonight. We catch some galaxies mid-embrace, others in the aftermath of dramatic encounters. Each tells us how gravity sculpts the universe. If the cosmos had tabloids, these objects would be our cover stars. We see their messy breakups, glowing makeovers, and dramatic new identities displayed across the night sky. In my field, a famous example is the antennae galaxies. They sit 45 million light-years away from us in the constellation Corvus. Through the lens, they look like two spiral galaxies caught in the act of crashing together. Their bright, overlapping centers shine intensely with starburst activity. Meanwhile, two massive tidal tails stretch outward like long insect antennae, earning their famous name. To an astronomer, these tails aren't just pretty flourishes. They give us pure evidence of stars and cosmic gas pulled into vast arcs by immense gravity. Inside these elongated streams, my colleagues and I found clusters of newly formed stars, glowing with a youthful blue light. It feels as though this deep space collision sparked cosmic fireworks, still blazing beautifully across hundreds of millions of years. The antennae act as our perfect cosmic laboratory for studying what happens when massive galaxies merge. Our observations across visible, infrared, ultraviolet, and radio light reveal a stellar system just brimming with chaotic activity. We watch dense pockets of gas collapse into stars at astonishing rates, carving out regions packed with vibrant young clusters. At the same time, the older stars get redistributed. We see them flung into fresh orbits that will eventually settle into a much calmer shape. Give it a few billion years, and the antennae will no longer look like two delicate spirals at all. They will relax into a single, massive elliptical galaxy. For us, what makes them remarkable isn't just their stunning beauty, but their perfect timing. We caught them at the exact right stage of collision. We get to witness the cosmic chaos and creation, the sweeping disorder and deep order all at once. Another absolute icon of galactic interaction we study is the Whirlpool Galaxy, officially known as Messier 51. Located about 23 million light-years away from Earth, it is a stunning, face-on spiral structure that looks almost too perfect to be real. Its graceful arms wind outward in flawless symmetry, glowing deeply with the light of billions of stars. But what truly makes the Whirlpool such a star on our cosmic stage is its ongoing, deep interaction with a smaller companion galaxy, NGC 5195. Through the eyepiece, this dwarf galaxy is visibly tugging on the Whirlpool's spiral arms, distorting them and triggering brilliant bursts of star formation. For astronomers like me, the Whirlpool and its companion remain one of the most stunning, photogenic sights in the entire night sky. Images from the Hubble Space Telescope reveal gorgeous dust lanes curving across those spiral arms like delicate, dark brush strokes. Glowing pink regions map out exactly where massive stars are forming, while bright clusters of blue stars highlight areas of very recent stellar birth. That smaller galaxy, despite being much less luminous to us, exerts a powerful gravitational influence. It drags material outward, giving the Whirlpool its slightly exaggerated spiral arms. If the Whirlpool were a Hollywood celebrity, its companion would be the mischievous partner bringing both the drama and glamour, completely reshaping its look for our cosmic cameras. The Whirlpool constantly reminds me that galactic collisions and interactions don't always need to be purely catastrophic to feel dramatic. I've seen firsthand how even a smaller galaxy can stir up spectacular changes in a larger one. In this system, the deep encounter has clearly enhanced the Whirlpool's beauty rather than diminished it. It gave the galaxy those elegant arms that make it one of the most studied spirals by my colleagues today. Over astronomical time, however, this relationship will deepen. The smaller companion galaxy will eventually merge fully into the Whirlpool, leaving behind a completely different, settled structure. But tonight, you and I get to just enjoy this cosmic show at its most dazzling stage. If the antennae are the explosive rock stars of our galactic catalog, and the Whirlpool is the glamorous movie star, we might consider the Cartwheel Galaxy the avant-garde artist. Sitting roughly 500 million light-years away in the constellation Sculptor, it truly is one of the most unusual galaxies astronomers have ever observed. Through my lens, its appearance is truly unlike any ordinary spiral or standard ellipse. Instead, we see a giant glowing wheel, where a bright ring of stars surrounds a central hub. Faint radiating spokes connect that ring right to the core, completing the breathtaking illusion of a cartwheel rolling silently through space. We know this cartwheel shape wasn't born from simple cosmic symmetry, but from a violently dramatic encounter. We believe a smaller rogue galaxy plunged right through its disk. That impact created huge gravitational ripples spreading outward through the stars and gas. I always picture these cosmic ripples acting exactly like the expanding waves on a pond after a stone is thrown in, heavily compressing the cold gas as they moved and igniting massive waves of star formation. That bright outer ring we observe is the leading edge of this ripple, softly glowing with clusters of newly born stars. For my team, it remains a striking example of how cosmic collisions reorganize matter into structures that are both scientifically fascinating and just visually extraordinary. Studying the Cartwheel Galaxy gives me quiet clues about the physics of how massive systems collide. The gentle waves of new stars sparked by the crash show me how shock fronts ripple through gas on massive scales. It reminds me just how creative the cosmos can be. It shapes forms that none of us could have ever guessed just by looking at simple math. You and I are looking at something that totally puzzled us at first, simply because it looks unlike anything else out there. Today, I see it as a true cosmic masterpiece, a rare star system that refuses to fit neatly into our little boxes. What ties the antenna, the whirlpool, and the cartwheel together isn't just their fame. It is their beautiful, stubborn individuality. Each one shows me a different peaceful stage of a cosmic crash. The antenna shows us the messy middle act, where long tails unspool and brilliant starbursts ignite. The whirlpool captures a gentle tug of war, with a smaller companion pulling a spiral into pure elegance. And the cartwheel shows the sheer art of cosmic meetings. A single punch right through the center changes a plain disk into something totally unique. Together, they show me the endless, beautiful things gravity can build when massive star systems cross paths. There are, of course, countless other examples drifting quietly across the deep night. But these specific shapes capture our imagination. They blend deep scientific meaning with pure, quiet beauty. These are the very galaxies you see glowing on posters, hidden in heavy textbooks, and on laptop screens. I like to think of them as the celebrities of the deep sky. We admire them for what they teach, but also for their grace. And just like famous couples, their quiet stories are full of messy tangles, long separations, and slow, grand changes. But I always remember that we are only seeing a quick snapshot. One day, the antenna will slowly melt into a much calmer shape. The whirlpool will eventually swallow its little partner. The cartwheel's soft, glowing ring will slowly fade as the ripples die and its stars grow old. The silent beauty we see tonight is temporary. It is frozen for a few 100 million years before slipping into a completely new form. But on a cosmic scale, that gives us more than enough time to just pause, look up, and wonder. When I study these glowing shapes, I am not just recording space oddities. I am slowly piecing together the long history of the universe itself. Every quiet crash is a deep clue to how stars are born, and how shapes larger than our wildest dreams grow from simple gravitational laws. The antenna, the whirlpool, and the cartwheel are not just lonely fireworks. They are quiet, beautiful chapters in the grand story of the night. Still, to me, they are much more than cold data points. They remind us that the deep cosmos is not just vast, but profoundly beautiful. If galaxies really are the famous couples of the dark universe, then these three hold the front page for a good reason. Their slow stories are dramatic, their glowing faces unforgettable, and their quiet legacies enduring. You and I can look up and see that even across billions of years and trillions of stars, there is still pure elegance and wonder. In the grandest ballroom ever imagined, they are the slow dancers catching the faint light, twirling gracefully while the universe watches. Deep at the center of almost every large galaxy, I find something strange and wonderful, a supermassive black hole. These silent giants weigh millions, or even billions of times more than our own sun, yet they hide in a dark pocket smaller than our little solar system. Invisible to my lens, they only show themselves by how they pull and bend their quiet surroundings. Stars whipping around at dizzying speeds, soft gas clouds glowing hot as they fall inward, and sometimes whole galaxies glowing from the energy of matter slipping into the dark, though these systems are huge oceans of stars and dust. In dark matter, their quiet centers are ruled by these tiny titans. They act like heavy anchors holding the entire dream together. The connection between a galaxy and its central black hole is beautifully profound. Through my telescope, I have seen that the weight of a supermassive black hole directly matches the heavy central bulge of ancient stars around it. A bigger star cluster means a much larger black hole. It points to a slow, beautiful cosmic partnership. Galaxies and black holes seem to grow together, quietly feeding each other across billions of years. When these massive systems finally collide, their hidden bond is tested in the most dramatic ways I can imagine. Picture two beautiful galaxies on a collision course, each hiding a supermassive black hole in its dark heart. As they gently draw close, their glowing stars and gas swirl into strange new paths, and heavy tides stretch them out. Over millions of quiet years, the galaxies slowly overlap, their dark centers drifting nearer and nearer. Eventually, the two dark giants are pulled into the exact same cosmic neighborhood. At first, they orbit each other from far apart, circling slowly through the merged galaxy. but gradually they spiral closer, losing a little energy with every single quiet pass. I often watch how two separate gravity wells slowly become a binary black hole system. Two giant masses locked in a slow, inescapable embrace. We know this cosmic dance can last for millions of years, but it eventually ends. As these black holes circle one another, I picture them warping the fabric of spacetime itself. Casting out ripples we call gravitational waves. These waves carry energy away into the void, causing their dark orbit to shrink just a bit. The closer they pull together, the faster they spin, throwing off stronger waves. In those last terrifying and beautiful moments, the two black holes whip around at near light speed, finally slamming together to form a single, massive black hole. The crash is so profound that, for 1 second, it blasts out more energy than every star, burning in our night sky combined. Only that raw power travels not as light, but as pure gravity. You and I know these waves as Albert Einstein's most astonishing prediction about our universe. Basically, they are physical ripples in space and time, washing outward exactly like gentle water rings on a pond after you drop a stone. If my telescope could actually see them, space would look like it was stretching and squeezing, down here on Earth. We are always being bathed by these faint cosmic ripples from distant dead stars. But they are far too weak to feel. As astronomers, we had to build incredibly precise tools to catch them, measuring shifts smaller than a single proton. Back in 2015, my colleagues and I finally did it. The LIGO observatory caught the absolute faintest whisper of two massive black holes colliding over 1 billion light years from our home. That little chirp lasted just a fraction of a second, but it proved to us that these space ripples were totally real. It also showed us that black holes, which I used to think of as just math on a chalkboard, actually exist, crash, and combine in the deep dark. Since then, we have logged dozens of these deep space echoes. Every single one is a quiet ghost story about heavy stars meeting their end. As whole galaxies crash together, their giant center voids follow. Though we measure this in eons, first they drift down into the new galactic center, dragging against the heavy pull of local stars and thick gas. Then they pair up, slowly spinning around each other until those gravity waves drain their final energy. For people in my field, this is our biggest challenge and dream. The hard part is actually spotting them, because even the loudest galactic crashes are barely a whisper against the endless dark. But here is the magic. Let's think about this together. These waves finally let us listen to the stars instead of just staring. When supermassive black holes finally meet, we expect them to ring the universe like a bell, sending out massive signals. My team is looking at future space gear, like the LISA satellite system, built specifically to catch those low and slow rumbles. Unlike our earthbound stations that just hear the fast chirps of tiny mergers, LISA will float up there tracking the slow, heavy bass notes of those ancient giants spinning together for long years. Listening to them will teach us exactly how galaxies swell up, how these dark objects eat, and how gravity acts under immense pressure. When I study these galactic collisions, the most beautiful thing is that black holes have two completely different faces. From one angle, they are violent monsters, crushing any wandering star that gets near. But from another, they are incredible artists, stirring up new stars and painting the night sky with light. As these two supermassive giants finally lock together, they do not just delete the past. They forge a brand new center point, anchoring the whole new galaxy and casting out ripples I can measure billions of years later. Now, picturing two giant dark stars colliding might seem scary to you, but we have to look at the massive scale. Even when our Milky Way eventually crashes into the Andromeda galaxy, their giant black holes will completely ignore our little blue planet. Long before those distant galactic centers actually touch and fuse together, our own sun will have burned through all its fuel, leaving Earth far too cold for any life. You and I will not be around to see that spectacular show, but studying these cosmic crashes has taught me one big lesson about the deep universe. It is incredibly patient. These shifts do not happen in years or quick centuries. They take millions, even billions of years. The cold orbits tighten, gravity ripples flow out, and finally there's one bright climax. Two unseen titans fuse into one. For me, it is a peaceful yet heavy story, proving that even the darkest dead stars add to the beauty of the cosmos. When I peer through my telescope, I just picture two quiet dancers circling in the dark, pulling closer with every slow spin. My observatory floor hums as I watch two distant giants step toward each other, meeting in a single graceful movement. That is exactly what galaxies carry at their cores. Not merely starlight and dust, but unseen heavyweights whose orbital steps send deep ripples across space and time. And while you and I might never witness this slow dance directly through a telescope, my instruments capture the deep music of their approach, echoing faintly across an endless, dark cosmic sea. When galaxies crash, the raw images I pull down suggest utter chaos, twisted spirals and vast, glowing arcs of deep space gas. Yet if we step away from that grand picture and zoom in on just one solitary star, the entire story completely changes. For the vast majority of stars, a galactic merger is hardly a violent upheaval. Instead, I see it as a sleepy drift, a gentle reshuffling of positions within an enormous cosmic city. It unfolds so gradually that nothing down here on Earth would ever realize it was happening above them. To grasp this calm silence, I always remind myself of the sheer scale of open space. Stars sit across such immense empty stretches that even as two giant galaxies completely merge, the odds of two suns colliding are practically zero. Imagine shrinking our sun down to glass marble. The nearest star, Proxima Centauri, would be another marble resting several hundred kilometers away. That is the deep emptiness I study every night. Distant galaxies appear packed with light, but in reality, they are almost entirely silent void. Because of this, a stellar collision is absolutely nothing like a sudden, violent car crash. It feels more like two slow, vast sandstorms ghosting through one another. The grains pass closely, but rarely ever touch. What I do observe is a slow shift in motion. A sun normally orbits its galactic core, anchored firmly by immense, combined gravity around it. When a neighboring galaxy approaches, that heavy gravitational field changes. I watch stars glide into new paths. Some stretch into massive tails, while others softly fall toward the central core. These celestial adjustments take millions of years. A sun tracing a perfect circle might stretch into a lazy ellipse, drifting calmly into a quiet new region. From the star's quiet view, nothing changes. It just sails onward, following a vast, invisible gravitational map drawn by the heavy cosmic structures moving around it. For a star like our sun, keeping its planets close, the story stays surprisingly peaceful. Our home star's local gravity easily overpowers the faint tug of any passing galaxy. Earth, for instance, orbits roughly 93 million miles from the sun. At that safe distance, the sun's hold completely dwarfs the weak pull of faraway stars. So when galaxies finally merge, planetary systems usually survive completely intact. Worlds just keep circling their quiet suns. Seasons fade and any alien life might sleep soundly, unaware that their entire home galaxy is being completely reshaped above. My charts do show some rare exceptions. If two suns brush too close during the merger, their gravity fields can powerfully clash, occasionally pulling or even ripping planets away from their safe orbits. A frozen world could be tossed into deep interstellar space, becoming a dark, wandering rogue drifting far from any warmth. But through my lens, such near misses are vanishingly rare. For almost every solar system, a galactic collision is a completely silent event. Sometimes I spot stars drawn out into enormous, sweeping arcs far beyond the galactic center, creating tidal tails spanning unimaginable cosmic distances. For those drifting wanderers, the galactic merger drastically changes their permanent place in the universe. A sun that once enjoyed the busy galactic suburbs might be flung into a dark, empty halo, circling the freezing outskirts for billions of years. Yet even in that cold exile, the star never actually shatters. It just keeps shining warmly, its deep nuclear fire completely unfazed by the impossibly slow ballet of galaxies spinning around it. As an astronomer, the quiet endurance of these ancient stars is a profoundly humbling reminder. Stars burn for millions or billions of years. Our sun, for instance, is gently resting halfway through its 10 billion year life. Over that immense stretch, giant galaxies will crash, blend, and completely transform. Yet our sun's steady, comforting glow will carry on untouched. From the perspective of a star, its galaxy is just a slowly changing backdrop. The stage scenery shifts softly, while the quiet performance simply continues. I always love finding the hidden silver lining. These massive collisions actually trigger the birth of new stars. As thick gas clouds from both galaxies slam together, they spark brilliant, deep space nurseries. These stellar newborns cluster together, burning with an intense blue fire, living incredibly fast, dramatic lives. To you and me, it is a crash. To them, it is exactly why they exist. Look through the lens with me. These suns only form when merging galaxies violently squeeze their gas. While ancient stars sit quietly in my telescope, this massive turbulence forces young stars to ignite, flooding deep space with fresh light. When I study these stellar tracks, I realize there is a profound serenity to it all. Whether my data shows a star drifting outward, pulled into a new orbit, or staying put, its daily life remains untouched. That deep, internal fusion just keeps burning. Hydrogen calmly fusing into helium, steadily casting a brilliant glow straight into our camera lenses. Gravity might shove or tilt it into some strange new path, but the star itself stays incredibly steady, a lone lighthouse piercing the violent galactic storm. Even when I detect supermassive black holes colliding at the galactic core, the outer stars barely even register the shockwave. They just keep burning, way too far from that central chaos to feel a thing. Deep space is staggeringly empty. These galaxies are so vast that violent cosmic fireworks actually miss almost every single star. It is an astronomical paradox. The brightest, most violent deep space events I observe are actually for the stars living inside them. Completely quiet affairs, like soft background music playing while they just go about their routines. As an astronomer, I find this calm endurance deeply poetic. You and I measure our human lives in simple days, years, and decades. We are fragile and fleeting. These stars measure their bright lives in eons. They easily outlast the chaos, glowing while entire galaxies warp and bend. Looking at the cosmos like this shows me a patience that is almost impossible to imagine. Change certainly happens, but it crawls so slowly that the star barely registers it, just burning on with the exact same quiet glow. I honestly find it comforting to model our own sun's distant future, riding along when the Milky Way and Andromeda galaxies finally crash into each other. Even as those huge galactic arms stretch out and their cores lock together, our sun will just keep on shining. Maybe Earth will still be in orbit, maybe not, but it will still pump out light to warm its tiny space. From the sun's point of view, there is no chaos, just quiet continuity. So what do you and I learn from all this? The night sky shows us that cosmic beauty isn't always explosive. Sometimes true beauty is just stubbornly enduring while the universe changes. Massive galaxies will smash together, twisting their shapes into totally new forms. But those stars just keep burning, steady markers in a wild sky. It is a masterclass in quiet, beautiful resilience. A deep lesson written right into the starlight that I capture from billions of years ago. When I observe two galaxies colliding, the first thing that jumps off the screen is their warped shapes. Huge spirals pulled into ribbons, long streams of stars thrown outward, and massive glowing bridges linking the two together. But the real magic I look for does not happen in the old stars. It is happening inside the massive, drifting clouds of gas and dust caught between them. You cannot see these massive reservoirs with the naked eye, but through my infrared scopes, they glow as the raw fuel for brand new suns. During a collision, these deep space clouds get violently shaken, crushed, and forced awake, sparking massive waves of star formation that completely light up our monitors. I know gas and dust sounds a bit boring at first. Space dust sounds like needing to sweep your floors, and gas feels just as ordinary. But looking through a telescope, they are pure magic. This interstellar gas, mostly raw hydrogen, fills the galaxy like a thin, invisible fog. And the dust grains, tiny flecks of heavy elements like carbon and silicon, scatter that light and create the gorgeous nebulas we photograph. Together, they act like cosmic soil growing new worlds. Without this material, the galaxies I map would be dead graveyards of old suns. Instead, they are active nurseries, pumping out fresh generations of stars. A massive galactic crash is just a cosmic gardener turning that soil. Lazy, drifting gas clouds get suddenly crushed together by intense gravity and violent, direct impacts with other massive clouds. My models show that under pressure, gravity finally wins the tug of war, forcing these huge clouds to collapse inward. Inside those collapsing zones, dense knots of matter quickly form protostars, igniting true nuclear fusion once they get dense and hot enough. So, out of this terrifying cosmic disruption, completely new light is born into the dark. In our field, we call these violent creation periods starbursts. During a massive starburst, I will see a galaxy forging new suns at rates dozens or even hundreds of times faster than normal. Galaxies that slept quietly for billions of years suddenly light up my telescope, blazing with fresh clusters of massive stars. These giants burn hot and bright blue. They pump out incredible energy but die young, usually detonating as supernovas in just a few million years. In their short, brilliant lives, they completely alter their deep space environments. Heating the surrounding gas, it seeds the void with heavy elements that will someday build future stars, planets, and maybe even living creatures. Let's look at this together. Starbursts aren't just dramatic to observe, they completely transform a galaxy's appearance. Through my lens, I see glowing pink and red regions, as deep space hydrogen gets ionized by raw ultraviolet light from young stars. When I study colliding galaxies like the antennae, dozens of these regions look like jewels scattered across their twisted shapes. Every glowing patch I map is a newborn star cluster. It proves creation thrives in chaos. Nebulae play the starring role here. These are the colorful dust clouds my colleagues and I photograph, like the famous Orion Nebula. During galactic collisions, extreme tidal forces stretch and energize these nebulae. Shock waves ripple through the gas, compressing filaments and igniting wild bursts of stellar formation. Seen through my telescope, these nebulae glow in vivid hues that map out different elements. Red means hydrogen, green is oxygen, blue means helium. To me, they look like cosmic gardens in full bloom, nurtured by the exact galaxy collisions that seem so destructive. Viewing these galaxies as cosmic gardeners is incredibly fitting. They scatter seeds of starlight into fresh clusters, quietly replenishing deep space with new energy and matter. Old stars die off, their remains enrich the interstellar dust with heavier atomic elements. Gravity then stirs that dust into new shapes, keeping the cycle of birth going. It is cosmic recycling on the grandest scale I know. Destruction and creation are locked together, and the sheer scale of this star birth is staggering. A single massive region sparked by a galaxy collision can hold thousands of brand new suns. Some will burn steady like our sun. Others will be brief, bright giants before collapsing into dense neutron stars or black holes. A rare few might even host planetary systems with the right conditions for life. It awes me that galactic collisions, dragging on for hundreds of millions of years, can actually plant seeds for future worlds. Stick with me here, the astrophysics behind this is beautifully elegant. As two galaxies interact, their combined gravity yanks on gas clouds, dragging loose material right toward their cores. This fast inflow feeds the supermassive black holes, igniting bright quasars, but it also packs the central regions tight, making deep space star formation explode. Meanwhile, I watch gas clouds in the outer edges clump together, sparking star birth in completely unexpected dark places. The final result is a galaxy dotted with frantic activity. A glowing patchwork quilt stitched entirely by gravity, but a starburst never lasts forever. This intense stellar birth burns through raw gas fast. Within a few hundred million years, the cosmic fuel runs low and the bright burst fades out. What remains on my monitors is a transformed galaxy, redder, quieter, and dominated by older stars. So collisions do not just create, they hit fast forward on galaxy evolution, pushing them through wild phases of activity right into more settled, quiet forms. The cosmic gardens bloom, the stellar harvest is gathered, and the soil rests until the next stirring begins. For us astronomers, watching these massive starbursts is exactly like catching the universe mid-sentence. They are extremely rare. Galaxies spend the vast majority of their lifespans drifting in much quieter phases. When I observe a galaxy in the throes of a starburst, I am glimpsing pure vitality, a burst of youth inside an otherwise slow, measured existence. It reminds me that galaxies, though ancient, still hold the capacity for sudden renewal, sparked entirely by the chance encounters of gravity. Sitting alone in the observatory reflecting on this, I find a deeply soothing balance here. The universe wastes nothing. Gas and cold dust that might drift forever are gathered into stars. Elements baked inside stellar hearts are blasted out by supernovae, only to build fresh suns and rocky planets. Galactic collisions look catastrophic through my lens, but they drive this grand cosmic recycling program. They are the cosmos's gardeners, turning the soil, planting seeds, and nurturing bright light where there was once only darkness. Even from Earth, millions of light years away, we can truly appreciate this cosmic beauty. Our telescopes reveal glowing arcs of starburst, vivid colors painted by young stars against black space. To me, every image is hard data, but also a masterpiece. Absolute proof that creation thrives, even during violent upheaval. You and I can see the universe is incredibly fertile, always sparking new light. In the quiet glow of a starburst, we glimpse the real truth of galaxy collisions. They are not just endings, but beautiful beginnings. Not just cosmic disruptions, but deliberate acts of cultivation. They prove to astronomers that the grandest structures undergo massive renewal, sowing new star generations that will shine for billions of years. Out here at the observatory, it feels like we watch galaxies slowly collide. Let's look at this together. These crashes keep deep space alive with light. Naturally, our eyes always catch the wild drama first. Those massive arcs of starlight, the bright pockets of new suns, and the fierce flares of feeding black holes. But the telescope tells us another side of the story. These cosmic crashes simply cannot last forever. Once the fireworks end and massive young stars burn out, I see these galaxies enter a quiet phase, a long stretch where chaos simply gives way to calm. What starts as a violent orbital dance eventually folds into one system, a shape carrying old cosmic scars, yet radiating a deep sense of steady balance. The raw aftermath looks completely messy on my screens. Long tidal tails whip into space. Stray stars scatter across the void, and gas clouds slam together, firing up new stellar nurseries. But over hundreds of millions of years, I watch these bright features slowly fade. The tails thin out as older stars fall back into the main core or scatter away completely. Bright bridges between the bodies snap, and those two sharp spiral identities blur into one. Gravity, patient and cold, drags everything toward perfect balance. As the merging finishes, those beautiful, fragile spiral arms are completely torn apart. Spiral arms need a flat, spinning disk to survive. The violence of the crash ruins that alignment entirely. So instead of those graceful pinwheels we map in astronomy, we get a rounded blob, an elliptical galaxy. These ellipticals look smooth through the lens. The stars pack into a thick sphere, losing their neat rings. Their glow leans heavy on the red, packed with billions of aging stars. The bright blue flash of youth dies off as giant suns burn out fast, leaving behind a dense cluster of older, cooler red stars. Turning into an elliptical shape like this marks a kind of cosmic maturity. The system survived utter destruction, renewed itself, and became something incredibly stable. To an astronomer, these old ellipticals act like the quiet elders of our night sky. They stop forming stars with that wild early energy. Their raw gas is just used up or blown away. Instead, they just burn softly with the combined light of truly ancient suns. They lack the flash of young spirals, but they hold a heavy dignity, a reminder that deep stability looks beautiful too. You and I have to appreciate the silence here. Past the roaring crashes and blinding starbursts, the galaxy falls into a long twilight of steady glow. Stripped of free gas, my instruments detect barely any colorful nebulas, very few hot young stars left to sparkle blue. Instead, the spectrum softens to a warm red. It is a sunset lasting for billions of years. When I track them, they show up as golden or crimson ovals glowing softly against the deep black. They might miss the sharp arms of a classic spiral, but they make up for it with sheer serenity. Deep inside tight galaxy clusters where crashes happen often, these old ellipticals absolutely rule. I find these swollen giants clogging the centers of massive clusters, fat from constant mergers. some of them hold over 1 trillion stars. These massive central bodies act as gravitational anchors for everything nearby. Surrounded by smaller satellite systems and fed by unlucky stray galaxies falling inward, their sheer bulk proves their violent history. Every single one is a graveyard of past unions, stars stolen from countless smaller victims. I read them as living records of ancient cosmic energy, written clearly in old starlight. But that smooth calm does not mean they are frozen entirely. Suns still trace long orbits. Supermassive black holes still hide in the cores, and faint dusty streams still drift inward from tiny neighboring galaxies. Still, compared to their younger days, these giant systems are completely settled down. The terror has faded into steady equilibrium. For billions of years, they sit frozen in time, glowing softly while their suns simply age. It is not empty silence, it is just deep cosmic contentment. Looking through the eyepiece, I often think this long galactic quiet holds a comforting lesson. Our own lives have those brutal moments of upheaval, wild bursts of energy where everything falls apart. But we can look up and remember this together. The universe proves that a quiet calm always follows chaos. These soft elliptical shapes glowing in the telescope prove that everything endures. Systems always find a new balance, even after total destruction. The journey to this quiet is just pure astrophysics. In a crash, star paths get completely scrambled. Beautiful flat rotations are traded for totally random, chaotic orbits. Look through my telescope and you'll see why ellipticals lack neat spiral arms. Their stars abandon the orderly paths that hold a disk together. Instead, I observe them swarming in every direction, filling a vast volume rather than a thin plane. What we see is a galaxy appearing perfectly smooth and round, lacking any preferred orientation. What looks so beautifully simple to us is actually billions of complex gravitational dances, finally settling into equilibrium. As astronomers, we know losing gas plays an equally important role. Collisions burn through gas in furious starbursts, while supernovas and black holes blow the rest away. With no fuel left for new suns, we watch the galaxy's glow shift entirely to older stellar populations. The youthful cycle of stellar birth slows down, leaving us to study a mature community of suns aging together. Without the chaotic drama of star birth, the galaxy dims just a bit, but in return, it gains deep stability, shining quietly through my lens for billions of calm years. We believe the most massive elliptical galaxies we track today are the final results of countless cosmic collisions, stretching all the way back to the early universe. Their staggering size, their perfectly smooth glow, and their empty star-forming regions tell me a story of massive ancient growth, followed by deep calm. When I peer at them, I am reading the final chapters of galactic evolution, where once turbulent systems finally rest in quiet grandeur. But don't mistake this cosmic silence for a dead zone. Through our instruments, we see stars inside these ellipticals still living out their fates. I watch some swell into red giants, while others collapse into white dwarfs, neutron stars, or black holes. Ancient globular clusters still orbit their halos, and I sometimes catch their central black holes flaring up when they swallow stray matter. Still, the overall rhythm we record is slower, less dramatic, beautifully measured. To an astronomer, spirals are youthful dancers in a cosmic ballet, while ellipticals are the enduring statues left behind when the music fades. We calculate this quiet stage will last for trillions of years, extending far beyond the lifespan of the universe as I observe it tonight. Long after the final spiral galaxies merge in my records and star formation completely dies, these ellipticals will still glow faintly with aging starlight. I view them as the ultimate survivors, grand galactic elders keeping watch over a darkening cosmos. To my eyes, their calm isn't a lack of action, but the glorious culmination of it. A lasting stability that proves to us how resilient cosmic structures are across truly unimaginable timescales. Staring up from the observatory, I realize the universe isn't just a loud engine of motion and energy, it is also a place of profound rest. Galactic collisions bring drama and starbursts bring brilliance, but as a scientist, I find the quiet aftermath deeply beautiful. The soft glow of elliptical galaxies is the pure light of endurance, shining steadily long after the chaos has cleared. That ancient light teaches us that even the most violent cosmic transformations eventually yield to calm. Like life itself, our universe holds not just raging storms, but long seasons of peace. Walk outside with me tonight and look toward the constellation Andromeda. Far across the dark sky, you will spot a very faint smudge of light. Without a telescope, it might seem completely unimpressive to you. Just a blur you mistake for a thin cloud, but I can tell you that dim patch is the Andromeda Galaxy, the closest massive galactic neighbor to our very own Milky Way. It is a spiral galaxy just like ours, holding hundreds of billions of stars, and my data shows it is on a direct collision course toward us. Speaking in cosmic terms, Andromeda isn't just passing through our neighborhood. It is hurtling straight for our galactic front door. Now, before you panic, my colleagues and I can assure you this dramatic encounter won't actually hit us for another 4 billion years or so. By the time it arrives, Earth's continents will have drifted into completely unrecognizable alien shapes. Our sun will burn much brighter and hotter, and humanity will either be long gone or living among the stars in ways I can hardly begin to imagine. As an astronomer dealing with a timeline this vast feels abstract, like waiting for a gentle breeze after thousands of star generations are born, burn out, and slowly die. Even so, knowing that two massive spiral galaxies like the Milky Way and Andromeda are locked into an inevitable collision fills me with sheer awe. We've carefully measured Andromeda's motion, and we know it's racing toward us at roughly 110 kilometers per second. That sounds like a terrifying speed, but when I factor in the vast distance, over 2 million light-years away, it becomes mathematically clear that this is a very slow, steady, majestic approach. Picture two colossal ocean liners slowly drifting together across an endlessly dark, vast sea. The distance is so immense, their meeting feels forever postponed, but I know the math, the outcome is inevitable. When the collision finally begins, the view will be spectacular. Any future astronomer looking up will watch Andromeda grow impossibly huge and bright in their night sky. Over millions of years, you and I wouldn't see a faint smudge anymore, but a blinding, luminous disk completely dominating the heavens. As astronomers, we know these galaxies will eventually collide, stars slipping past each other like ghosts. The mathematical odds of actual stars colliding are vanishingly small, given the immense emptiness between them. Instead, for us observing, the real beauty lies in the slow warping of those immense galactic structures. In the massive tidal streams of ancient stars stretched wide, and the sudden blaze of new stellar nurseries igniting. This cosmic merger will not be a sudden crash, but a prolonged embrace. That first close pass will fling massive tidal tails of dust deep into space. Then, as relentless gravity pulls them back, these spiral galaxies will collide again and again. Each sweeping pass violently stirring their deep cores and reshaping them. This slow celestial courtship will play out over billions of years, finally settling into one massive structure. My colleagues and I predict the result is a giant elliptical galaxy. Rounder, smoother, and vastly larger than either of its parents. In our field, we playfully call this future home Mylomia. For you and I, the most fascinating question here is what happens to our little solar system. The data shows it will not be destroyed, but our exact address in the galaxy could drastically shift. Our sun and orbiting planets might be flung deep into the outer halo or pulled inward. We could even wake up inside a massive tidal tail, drifting slowly through a sparse, isolated stream of stars stretched thin across space. For any distant human descendants, whether they inhabit Earth, Mars, or some yet undiscovered exoplanet, their view of the night sky would be completely unrecognizable. The constellations I map every night would be erased, replaced by strange star patterns during this cosmic shuffle. If Earth remains habitable, the view from our observatories would be unlike anything humanity has ever witnessed. Just picture looking up to see two massive spiral disks overlapping, their arms weaving glowing threads of starlight. Imagine newly ignited starburst regions glowing so intensely they completely wash out the deep space background. It would be a sky completely alive with motion, though moving on astrophysical timescales far too slow for any human to perceive. Generations would pass, entire civilizations would rise and fall. And still Andromeda's vast structure would only gradually shift from decade to decade. This deep space drama unfolds with the absolute patience of eternity. This approaching collision between our Milky Way and Andromeda teaches us something fundamental about the universe. It proves that galaxies are never isolated islands. We are all deeply connected in a vast cosmic web. Gravity guarantees that no star system sits entirely alone. Given enough time, galactic neighbors always drift together, collide, and violently merge to create new forms. What is happening to us is completely normal. It is part of a grand astrophysical pattern, playing out countless times across deep space. Through my telescope, I see heavens filled with elliptical galaxies, silent, ancient wreckage from past cosmic mergers. It is incredibly humbling to realize our Milky Way, with all its familiar constellations and quiet spiral arms, is strictly a temporary arrangement. We are simply living in a brief cosmic snapshot, a fragile moment where our galaxy holds its familiar shape. In a few billion years, that fleeting snapshot vanishes entirely, replaced by a transformed sky where the Milky Way as we observe it no longer exists. The same stars will shine, but the galactic stage will have been entirely rebuilt. If astronomers find any humor in this, it is definitely in the sheer scale. We stress over simple daily schedules, weekend plans, or a slow internet connection. Meanwhile, astrophysics tells us the universe has already penciled in an unstoppable meeting, an encounter immense enough to reshape hundreds of billions of suns. And the best part, my models say it begins in 4 billion years, give or take a few hundred million. That is about the most gentle deadline deep space ever offers us. Plenty of time to finish whatever earthly errands you have this week. As a scientist, Andromeda looming on our horizon is not something to fear. It is a genuine marvel. It proves we inhabit a constantly evolving universe. It shows me that massive change is built into space-time, and eventually, even the greatest galaxies must transform. The future of our home galaxy is literally written in Andromeda's slow, steady approach. But from my observatory, this is not an ending. It is a beautiful continuation, reshaping everything into a grander stellar structure. So tonight, when you and I look up at Andromeda's faint smudge, remember we are witnessing pure cosmic destiny. That ancient, soft starlight has already traveled over 2 million years just to reach our lenses. And behind that light is a gravitational force so vast, it will one day entirely redraw the map of our home galaxy. Look up with me, time's horizon is long, but this meeting is inevitable. Two star cities drifting across the deep will one day unite. From their collision, a new galaxy will rise, glowing silently in that endless night. In my line of work, we've gotten quite good at one specific thing, simulating the future. From tracking weather to charting planetary orbits, supercomputers act as our crystal balls. They show us exactly what nature's laws will eventually unfold. And when we model the cosmic destiny of our own Milky Way, my colleagues and I peek billions of years ahead. We watch and fast forward as our spiral home drifts toward its massive neighbor, the Andromeda Galaxy. Our data reveals a story that is both dramatic and strangely elegant. It is a cosmic performance our descendants might never see in person. Yet we already grasp its details. The secret behind my work is simple physics. You see, galaxies are never just random clouds of stars. They are locked together by gravity, held by invisible dark matter, and driven constantly by the sheer momentum of their own drift. Every single star, gas cloud, and dark halo is gently pulled by the quiet, steady hand of gravity. To model a galactic merger, I start by feeding everything we know about the Milky Way and Andromeda, their mass, their shape, and their speed, straight into our supercomputers. We lock in those numbers and let the equations of Newton and Einstein take over. What plays on our screens isn't art, it is the pure mathematical choreography of gravity. The results are completely astonishing. In my models, Andromeda doesn't just slam into our galaxy and stop. Instead, the two galaxies weave together in a long, slow embrace. During their first close pass, gravity rips out long streams of stars, stretching them into massive arcs that glitter across the dark. They pull apart, dragged back by their own mutual gravity, before swinging in again. This slow cosmic dance repeats. each pass stripping away more shape until finally the two giants melt into one. Start to finish, this process takes several billion years, an absolute eternity to us, but just a quiet, natural cycle in the cosmos. One thing that always amazes me in these models is that individual stars stay safe. You and I might easily picture suns smashing together in fiery crashes. But space is remarkably empty. Even inside a galaxy, the gaps between stars are so huge that direct hits almost never happen. Instead, the stars just glide past, their orbits gently nudged by the shifting gravity of the merger. A sun that used to circle our Milky Way core might get tossed outward or dragged into a totally new path, but it survives the event completely intact. From a star's perspective, this collision is just a gentle reshuffling, not a disaster. For our own Earth and Sun, my data shows survival isn't just possible, it's highly likely. Our solar system might get thrown into a wider orbit or drift down a tidal stream, but it won't be destroyed, though whether our planet is still habitable by then is a very different question. 4 billion years from now, our sun will burn much hotter, slowly baking the Earth and likely boiling away the oceans. The climate will shift beyond recognition, probably long before our galaxy ever makes first contact. If anything is still alive here, it will have adapted to the heat or moved to other planets. Still, imagine the night sky during that merger. It would be breathtaking. A shifting canvas of starlight unlike anything we've ever seen. My simulations let us picture this exact transformation in stunning, quiet detail. I've watched countless digital Milky Ways crash into virtual Andromedas. Every single pixel on my screen holding millions of suns. We can rotate the model, seeing the galaxies from deep inside the core or from way out in the dark as a silent cosmic spectator. In most of my digital runs, the Milky Way loses its delicate spiral arms. Torn and twisted until they look like ribbons blowing in the wind, Andromeda is stripped bare too. What we see emerge after countless encounters isn't a spiral at all. It becomes an elliptical galaxy, a massive, rounded ball of ancient stars with a soft, smooth glow. We've even given this future galaxy a working name. Milkdromeda, a playful mix of Milky Way and Andromeda. Some call it Milka, but either way, it's destined to be a heavyweight. It will hold over 1 trillion stars, easily doubling the population of its parent galaxies. It'll shine brighter, stretch wider, and completely dominate our corner of the universe. When you and I look at deep cosmic history, this merger is just one more step in a long line of unions, quietly shaping our universe. But for those of us living inside one of these merging galaxies, it feels deeply personal. When I look at our computer simulations, the true hero is invisible dark matter. We know this unseen mass makes up most of both galaxies, forming giant halos that stretch way beyond the starlight we can actually observe. As our Milky Way and Andromeda approach, these dark halos hit first, overlapping in the dark like two giant, ghostly spheres. That intense gravity then pulls the visible stars together, guaranteeing the two galaxies will inevitably fuse. If that dark matter wasn't there, our galaxy and Andromeda might just sail past each other in the cosmic night. Instead, they are locked together by unseen chains, and Andromeda isn't the only player in this cosmic event. Our smaller galactic neighbors, like the Magellanic Clouds and the Triangulum Galaxy, along with countless faint dwarf galaxies, are caught in this gravitational net. We expect them to get swallowed whole or scattered into glowing tidal streams. The resulting Milkdromeda galaxy won't just be two huge spirals. It will be a massive structure holding all those smaller, absorbed companions. Like a stellar family tree with countless branches, our future galaxy will hold the ancient legacy of every tiny system it ate. As an astronomer, I find real poetry in watching these models unfold. On my screen, billions of years unfold in mere minutes. I watch a spiral galaxy spin like a pinwheel, smash into its neighbor, and completely rebuild itself right before my eyes. Something no human could ever live to see becomes a beautiful tale of glowing light trails. For us, these aren't just data models, they are literal windows into the universe's ultimate fate. They remind my colleagues and I that outer space is constantly shifting, forever evolving, and always waiting to stun us with its sheer scale. Sitting in the dark observing this, I can't help but feel a profound sense of cosmic humility. Here we are, projecting the fate of the cosmos 4 billion years out. Sometimes I struggle to plan my weekend, yet our ability to map out these deep futures is a massive triumph of human curiosity and science. From chalk on a blackboard to supercomputers running trillions of calculations, my field has built a clear window into tomorrow's universe. You and I know that when the Milky Way and Andromeda finally collide, there won't be a traditional audience watching. The stars certainly won't stop to clap, and distant galaxies won't pause their own rotations to care. The impact will just silently happen, just like thousands of other cosmic mergers I've studied, and thousands more to come. But thanks to the data crunching in our labs, we've essentially already seen it. We know exactly how the major beats of the story go. The violent stretching of spiral arms, the long tidal tails of gas, settling slowly into a giant elliptical shape. Andromeda will rise, shining quietly in the void, proving that deep space is always changing. Honestly, for an astronomer, that's the most beautiful realization. By mapping out this distant timeline, we don't just predict the future. We learn to appreciate the night sky we have right now. This Milky Way we observe, with its sweeping arms and rivers of starlight, is just a temporary phase in a much grander timeline. Eventually, the constellations we chart will vanish, remade into something entirely new. Yet, as I crunch the numbers, I find comfort in that. Stars burn out, galaxies evolve, and the cosmos keeps dancing its slow waltz whether my telescopes are looking or not. Looking back across cosmic history, galaxy collisions aren't rare, dramatic flukes. They are a totally standard part of how the universe grows. Let's travel back together just for a moment to the early days of the universe. Just after the Big Bang, about 13.5 billion years ago, cosmic matter simply hadn't expanded very far into the void yet. Space was far smaller and incredibly dense. The galaxies back then weren't the gorgeous, wide spirals or massive ellipticals I photograph today. Our data shows small, clumpy little structures, loaded with raw gas and pumping out stars at a crazy pace. Because they were sitting so close together, frequent collisions were completely unavoidable. I like to think of them as young seeds planted in a tight garden. With zero breathing room, their stellar roots were constantly tangling up. When my team and I point instruments like Hubble or the James Webb Space Telescope at deep space, we often find galaxies that look bent, totally irregular or chaotic. We know these aren't random mistakes or bad cosmic design. They are literal snapshots of star systems actively growing and smashing together. What seems like a mess through the lens is just the universe building the giant galaxies we observe today. And trust me, these ancient galactic impacts were never gentle. Because early systems were small and packed with gas, every collision triggered explosive bursts of new star formation. Gas clouds slammed hard, compressing under intense gravity and igniting into brilliant waves of brand new stars. We call these events starbursts. They forged blinding clusters of massive stars that detonated as supernovas just a few million years later. Through our telescopes, those fireworks appeared beautiful yet violent, forever reshaping their host galaxies. Over epochs, this endless cycle of mergers and starbursts slowly transformed tiny, messy star clusters into grand, organized galaxies. We astronomers call this beautiful process galactic assembly. Think about how we build cities, not overnight, but by joining small towns together. As an observer, I see the universe building massive galaxies the exact same way. Every single star system we map today was born from countless, quiet cosmic collisions. Even the most elegant spiral structures hide a chaotic past deep inside their stars. If you and I could peel back those glowing layers, we would find swallowed companions. Torn stellar streams ripped from ancient neighbors, and deep scars left by violent encounters. Our own home galaxy is no exception. When I study the stellar halo surrounding our Milky Way, I find the lingering ghosts of ancient galaxies, quietly absorbed billions of years ago. We identify these lost siblings by tracking their stars' unique chemical fingerprints. Stars born far away carry special blends of heavy elements. It all depends on the deep history of supernovas and star births inside their original homes. By analyzing those faint stellar signatures in the lab, we have mapped our galaxy's family tree. The data shows our home has quietly swallowed dozens of smaller star clusters over eons. We are literally sitting on a pile of cosmic leftovers, woven into one glowing spiral. To us in the field, collisions completely define how space takes shape. Without these impacts, everything would have stayed tiny and formless, just glowing crumbs scattered everywhere. Instead, these slow mergers let galaxies grow huge, pulling in enough dust to become orderly. Those beautiful spiral arms formed as loose gas calmed down into spinning disks after crashing. I often see giant elliptical galaxies. They form when two spirals violently crash, scrambling their billions of stars into smooth, featureless spheres. That is how the deep void sculpted pure variety out of chaos, creating the gorgeous galactic zoo we observe nightly. What fascinates me most is how these collisions spread heavy elements around. Those very first primordial stars burned almost purely on hydrogen and helium. They were just simple ingredients forged right at the Big Bang. But through massive supernovas, especially the ones sparked by crashing island universes, heavy metals like carbon, oxygen, and iron were thrown across the dark. Those atoms seeded the next generation of stars, and eventually solid planets. If these giant collisions had not stirred the cosmic pot and sparked new stars, space would never have gained the complex chemistry needed to create biology as we know it. In my line of work, we see that ancient violence actually birthed cosmic fertility. And let us not forget how those early crashes also fed supermassive black holes. We find these dark titans anchoring almost every core. Some weigh millions or even billions of times more than our sun, but our models prove they did not start out that heavy. They started as tiny gravitational seeds, probably just the collapsed remains of dead hypergiants. When those galaxies slammed together, their central black holes swallowed massive rivers of disrupted gas falling inward. Those feeding frenzies let them grow incredibly fast, turning into the massive gravitational anchors we detect now. Sometimes these mergers pushed two black holes together, trapping them in a fatal inward spiral until they fused. Those invisible collisions sent ripples rolling across spacetime itself, faint echoes that my colleagues at LIGO and Virgo are just now beginning to hear. You and I can find proof of this violent, beautiful history everywhere if we just look closely. My deep sky surveys catch galaxies mid-crash all the time. I see faint tidal bridges stretching between them, all the way up to smooth ellipticals hiding their pasts. Right next door, I map faint star streams arcing above the Milky Way. Ghostly remnants of neighbors we completely shredded and absorbed. I often observe Andromeda's deep scars too. Its giant loops and stellar shells encircle the main disk exactly like ripples fading on a quiet pond. We treat these structures as cosmic fossils. They are silent witnesses to the endless impacts that built reality. What humbles me most about this science is the massive scale of time. Back in the young universe, these crashes were totally routine, dragging on for hundreds of millions of years. To human minds, that sounds impossible, but cosmically it was a fast, furious era. As space expanded and things grew apart, the crashes slowed down, though they never truly stopped. Tonight, local galaxies drift farther apart, yet I know their ultimate fates remain deeply intertwined. These majestic mergers unfold in slow motion, absolutely certain, driven by gravity's cold, patient pull. Looking through these lenses with you is honestly like watching the whole universe grow up. Let's look back together. The early universe was a rowdy, crowded playground, with young galaxies colliding and sparking massive stellar tantrums. Over billions of years, we see these galaxies mature into much calmer, stable shapes, though their restless energy never truly faded away. Through my lens today, I still watch collisions happen, just on a grander, quieter scale. The cosmos simply never outgrew its habit of rearranging things. It just slowed down. When I study this cosmic history, I realize these galactic crashes aren't just disruptions, they are the true engines of creation. They push entire star systems to grow, seed outer space with the building blocks of life, and keep our universe beautifully active rather than frozen. Every single star, planet, and even us, we are all born from this endless, ancient chain of deep space encounters. When I look up at the night sky, I'm watching billions of years of cosmic impacts, all woven into the serene galaxies drifting high above my observatory. This quiet beauty of the modern cosmos hides a deeply violent, turbulent past. Yet that exact turbulence is what made this beauty possible. Without those early galaxy crashes, I wouldn't have great spiral arms to map, stable worlds to study, or a mind to wonder about where we came from. It reminds me daily that total chaos can spark perfect order. From the rough jostling of countless star clusters, the grand architecture of our whole universe took shape. When galaxies crash, we usually talk about sweeping arcs of starlight, giant gas rivers, and shifting shapes. But beneath all that massive grandeur, I observe a much more intimate story, unfolding right inside the hearts of individual stars. Every single star, whether it's dragged into a massive cosmic collision or left drifting entirely alone in the void, ticks away to the beat of its own internal clock. Its final destiny relies on gravity pulling deeply inward, while nuclear fusion pushes fiercely outward. So while galaxy mergers might build the dance floor, the stars I track always carry the rhythm of their own lives. For you and me to really grasp this, let's break down a star's natural life cycle. Stars are born when freezing hydrogen clouds cave in under their own gravity. They heat up until nuclear fusion sparks right inside their cores. For the vast majority of its life, a star sits perfectly steady, quietly burning hydrogen into helium in a delicate balance. Take our sun, for example. It's been burning steady for about 4.5 billion years, and it should keep going for roughly 5 billion more. In astronomy, we call this the main sequence. It's a long era of calm where stars glow evenly, warming any small planets that happen to orbit them. But absolutely nothing in deep space lasts forever, and stars are no exception. Once that core fuel runs dry, radical change is coming. For an ordinary star like our sun, the next phase is mutating into a massive red giant. When hydrogen drops too low, that internal fusion slows and gravity takes over. The core shrinks tightly and heats up, forcing the outer layers out into a swollen, glowing balloon. An average-sized star can blow up enough to swallow nearby worlds. If our sun did this right now, its fiery edge would easily eat Mercury, Venus, and probably Earth. From my telescope way out here, it would just look like an impossibly huge glowing ember, burning deep red. In astrophysics, red giants mark both a tragic ending and a fresh start. As they swell up, they cast off their outer skin into the void, blowing bubbles of gas that float away like faint, glowing halos. Lit up by the dying core's faint light, these colorful shells form what we astronomers call a planetary nebula. It's a terrible name, honestly, because they have nothing to do with planets. They're really just markers of stellar death, hauntingly gorgeous clouds that glow for tens of thousands of years before finally fading out completely. Through my spectrograph, I watch those fading clouds recycle cosmic dust, heavily salting our galaxy with rich elements cooked up during the star's life. Deep inside that glowing nebula sits the bare, leftover core of the star, a heavy white dwarf. These things are pure stellar corpses, unbelievably dense, completely dead, with zero fusion left inside. I can spot a white dwarf no bigger than Earth, yet it holds the crushing mass of an entire sun. Their surfaces only glow from leftover heat. Over billions of years they cool down entirely, turning into black dwarfs, objects so utterly dark they vanish from sight. Think about this with me, none even exist yet because our universe just isn't old enough. Right now, every white dwarf still gently glows, like fading fireplace embers. But for much heavier stars, the ending is far more violent. Stars several times heavier than our sun burn fast and die young, tearing through their fuel with a wild, reckless intensity. Instead of calmly swelling up, these absolute titans explode outward into massive red or blue supergiants. They are colossal monsters that burn fiercely but briefly. When fusion finally fails them, gravity drops the hammer with one last, universe-shaking blow. Look through the lens with me. A dying stellar core collapses, blasting its outer layers into a brilliant supernova explosion. We measure the flash. In one instant, that star unleashes more energy than our entire galaxy does all year. To an astronomer, supernovae are the most stunning cosmic events, blazing bright across millions of light years. In my field, we know they aren't just stellar deaths, but seeds for new beginnings. From the chaos of observation, I see them scattering heavy elements like carbon, oxygen, silicon, and iron across deep space. the very materials destined to form new planets, vast oceans, and living beings. I picture the galaxy as a gardener. Supernovae are the cosmic scatterers, flinging the raw ingredients of life far out into the dark void. When I examine the remnant core, its fate depends entirely on the original mass. A modestly sized star will simply collapse down into a dense neutron star. These are truly extraordinary objects, measuring just 20 kilometers across. Yet they pack more mass than our sun. My calculations show a mere teaspoon of this matter outweighs mountains. They are so dense, their surfaces literally warp passing light. And through our instruments, we watch them spin hundreds of times per second, sweeping intense beams of radiation outward like massive cosmic lighthouses. If the star I'm tracking is truly massive, its core simply collapses beyond all physical resistance, becoming a black hole. Here, my models show gravity overwhelming every other force, dragging matter into a region so terrifyingly dense that not even light escapes. The black holes we observe forming from supernovae might only hold a few solar masses. Still, I see their influence reach far beyond their small size. They shape surrounding galaxies, and during massive collisions, they drive the deep evolution of the cosmos. When we map galactic collisions, these individual stellar fates remain surprisingly steady. Space is so vast that the stars rarely collide directly. Their lifespans just unfold exactly as their mass and internal structure dictate. But collisions absolutely dictate how many stars ignite and where. As I watch galaxies merge, huge gas clouds compress, triggering massive, brilliant bursts of new star formation. Every newborn star simply inherits the long, quiet arc of stellar destiny. Fated to shine, slowly expand, and eventually die, exactly like the countless generations before them. To an astronomer, collisions are a beautiful trigger. They ignite entirely new generations of stars, each carrying its own unique story of cosmic transformation. Over deep time, tracking this interplay between collisions and star life reveals a beautiful, unending cycle of creation and violent destruction. You and I can step outside tonight, and most of the stars we see were likely born inside those turbulent cosmic crashes. From my observatory, I know some will eventually explode as supernovae, violently scattering the heavy elements needed to fuel the next round of star formation. Others will just quietly fade into small white dwarfs, adding to the faint glow of galactic halos. Sitting at the telescope, pondering these fates feels deeply reflective. While the galaxies I study survive for tens of billions of years, a star's life is comparatively fleeting. They flare into existence, burn through their fuel, and transform into strange new objects. Yet as I analyze the data, their endings are never wasted. The dust and gas they return to space become the exact raw ingredients for future solar systems. In the cosmos, every ending is a beginning. Every stellar death sparks new creation. Through my lens, galactic collisions are less about destruction and much more about profound cosmic renewal. They violently shake the cosmic snow globe, churning up gas and dust, striking the match for star birth, and setting countless new stellar lives into motion. I spend my nights tracking those quiet dramas, red giants swelling, white dwarfs fading into the dark, neutron stars spinning, and black holes silently consuming everything. The universe has always been a patient recycler. Nothing I measure is ever lost, only beautifully transformed. The iron in our blood was forged in ancient stars that died billions of years ago, likely inside galaxies that have long since merged and been entirely reshaped. When I reflect on the final fate of these stars, especially during massive galactic collisions, you and I can see the cosmos isn't a place of simple endings, but a vast theater of perpetual change. Stars burn out and galaxies crash, but from that cosmic debris comes new life, new light, and the beautiful continuing story of the universe. Tracking these stellar life cycles night after night reminds me of something deeply profound. Even in the grandest collisions we photograph, the fate of stars is written not in chaos, but in deep continuity. I see every star's journey as a single thread. Collisions simply weave those threads into much larger, brilliantly complex patterns. What registers as an ending on my instruments is always the beginning of something new. It's a lesson baked into the very fabric of the cosmos. When we first started studying these grand galactic collisions in heavy detail, We fully expected normal gravity and gas dynamics to be doing all the heavy lifting. We figured stars would just drift by, gas clouds would smash together, and the galaxies would slowly merge into entirely new shapes. But as our modern telescopes grew sharper, and our ways of mapping mass distribution improved, a highly curious pattern emerged. We realized something invisible was actively shaping these events, an anomaly far more massive than all the glowing stars and gas combined. I call this hidden hand dark matter, the silent framework of the cosmos. It refuses to shine, reflect, or absorb any light. It completely ignores light. That makes it totally invisible, even when I peer through the most powerful deep space telescopes. I sense it only through gravity, feeling its gentle tug on stars, watching it bend distant light, and gripping cosmic structures that would otherwise scatter. When I watch galaxies collide, dark matter always plays the starring role. Without it, the vast drama of cosmic collisions changes completely. The universe you and I live in simply would not exist. The best proof I have seen comes from a system we call the Bullet Cluster. Floating roughly 3.8 billion light-years away, it shows the glowing aftermath of two massive galaxy clusters crashing at high speed. To me, a single cluster is already staggering, hundreds of massive galaxies softly bound together by a deep gravitational pull. When two of these giant swarms collide, they give me a perfect, natural lab to study the unseen scaffolding of space. What makes the Bullet Cluster so profound is that it handed us direct, observable proof that dark matter is real. Looking through X-ray telescopes, my team mapped the hot gas filling the space. It glowed brilliantly as the impact heated it to millions of degrees. This sweeping gas makes up most of the visible matter out there. It easily outweighs all the glowing stars themselves. During the Great Crash, those massive gas clouds violently slammed right into one another, slowing down, piling up right between the clusters exactly like cars stuck in thick traffic. But when I used a clever trick called gravitational lensing to map out the sheer mass inside, I noticed something absolutely astonishing. Lensing happens when ancient light from far-off galaxies bends around the heavy gravity of the mass sitting directly in its path. By carefully watching those background galaxies stretch and distort, I could draw a clear map of exactly where the hidden mass rested. My map showed that most of the mass coasted right through the collision. It hovered around the galaxies, nowhere near the piled-up hot gas. So while all the visible matter, that glowing gas, hit the brakes during the crash, the vast majority of the real mass ignored the impact completely. It simply drifted through, totally unaffected. This phantom mass perfectly aligned with the galaxy's new positions, proving there was way more stuff out there than just stars and gas. For me, the final conclusion was simply inescapable. Dark matter must exist, a ghostly companion shaping galaxy evolution from the shadows, yet never actually colliding. To this day, the Bullet Cluster remains my absolute strongest piece of evidence for dark matter. It showed me a literal split between the glowing visible matter and the vast, heavy bulk. Without dark matter, my maps would just trace the hot gas. Instead, they revealed deep, invisible clumps of weight, betraying the presence of something completely unseen. For me and my colleagues, this was the smoking gun. These deep space crashes showed me a vital secret: dark matter hardly even interacts with itself. While normal matter violently crashes, burns, and stalls out, I watch dark matter glide through other dark matter halos without any friction. This strange behavior tells me it is made of phantom particles that almost never touch, interacting purely through a gentle gravitational pull. That is exactly why galaxies can pass right through each other, without their protective dark matter halos shattering to pieces. To my eyes, the galaxies wear invisible cocoons that smoothly overlap, yet never truly tangle. Dark matter is no simple background player, it is the very stage. Our galaxies sit perfectly embedded inside massive dark matter halos. And those heavy halos provide the steady gravitational anchor, holding everything together. Without this unseen weight, galaxies would completely fail to keep their shining stars from drifting away. I observe spiral galaxies rotating much faster than their visible matter alone should ever permit. Without that extra invisible grip, they would violently fling themselves apart, just like spinning pizza dough tossed a bit too thin. During collisions, dark matter guides their exact paths and perfectly shapes the final cosmic merger. You and I can see its power. It provides the pull keeping galaxies bound while gas strips away and stars fling outward. The smooth, elliptical galaxy that eventually forms is literally sculpted inside this dark matter cocoon. To me, it acts as both a safe container and a gentle guide. The bullet cluster is not the only place where I have seen dark matter revealed during a massive collision. Other brutal smash-ups, like the famous train wreck cluster, also called a Bell 520, show strange dark matter layouts that still leave my colleagues puzzled. So what do you and I make of this? Sometimes it clumps strangely, challenging my simple models and hinting that the dark cosmos is far stranger than I ever thought. Every cosmic crash I observe becomes a test case to understand this shadow universe. What truly humbles me at the telescope is that dark matter is about 85% of everything out there. Yet it remains entirely unseen and deeply mysterious. Everything my telescope catches, the stars, planets, and glowing gas clouds, is just a tiny fraction of what is actually out there. Think of the visible universe as nothing but sea foam on a wave. Dark matter is the vast, deep ocean beneath it, driving the current but forever hidden. Look through the lens with me. When massive galaxy clusters pass right through one another, we finally get to watch dark matter work. The glowing matter drags and slows down, while the dark matter just keeps going. That split tells us everything. By mapping these quiet cosmic accidents, my colleagues and I hope to finally unmask it. We suspect they are exotic particles that barely touch normal matter. We call them WIMPs. Short for weakly interacting massive particles. Some of us also hunt for lighter axions. Either way, the slow-motion wreckage of these galaxies proves there is something massive out there in the dark. Spending nights staring at these images, I have come to see dark matter as the universe's silent architect. It never lights up our night sky. It never explodes in a brilliant supernova. It does not forge the glowing stars that calm us to sleep. Yet without its heavy pull, those beautiful spiral galaxies would never exist. Even the most violent cosmic collisions are guided by its unseen gravity. Every sweeping arc of light, every sudden flash of star birth, and the eventual peaceful settling of a newly merged galaxy happens within its frame. I find it beautiful, really. Something entirely invisible holds our whole universe together. Observing the famous bullet cluster proved to me that space has hidden layers. It showed us that violent impacts can actually expose those invisible bones. While clouds of gas smash together and stars glide past, the dark matter simply drifts on, completely unbothered. It is the heavy, quiet floor beneath this endless cosmic waltz. It acts as the ghost partner, guiding galaxies through their slow waltz. These massive collisions remind me of how painfully blind we still are. Starlight might look dazzling through the eyepiece, but the real weight hides in shadow. This strange, elusive mass refuses to show its face, but I can trace its cold hands in the twisted shapes of ruined galaxies, in the warped bending of ancient light and the deep, enduring structures of space. Through the sheer violence of a collision, it whispers from the dark, silently pulling the strings from behind the curtain. Let's change our focus for a moment. When galaxies crash, it looks like a grand show of glowing gas and stretched out stellar tails. Yet buried deep in the center of the wreckage is a completely different story, one much harder to see, but infinitely more violent. I am talking about supermassive black holes, the heavy, sleeping giants sitting at the heart of almost every galaxy we map. On a normal night, they rest in quiet darkness, taking tiny sips of stray dust. But when two star systems finally crash, the cosmic floodgates fly open. These dark monsters wake up and feast, growing so rapidly that they permanently alter the glowing brightness of their entire galaxy. Right in the core of almost every huge galaxy, including our Milky Way, sits a supermassive black hole. They weigh anywhere from millions to billions of times more than our own sun. People think of them as hungry monsters, but they usually stay perfectly quiet. I study our own central black hole, Sagittarius A star. It is a very polite eater, just casually nibbling on scraps. But during a galactic merger, that calm completely shatters. The freezing gas and dust that used to orbit so peacefully gets whipped into absolute chaos. Intense gravity pulls hard on these thick clouds, violently dragging everything down toward the core. This inward rush is everything. Black holes rarely ever swallow whole stars. The empty space between them is simply way too wide. They actually feed on gas, and a galactic crash acts like a massive cosmic delivery truck. Those exact same gravitational waves that stretch out glowing stellar tails also work like conveyor belts, shoving huge clouds of matter straight into the hungry center. As all this material spins downward, it forms a blazing ring around the black hole. Deep friction heats that spinning gas to millions of degrees, blasting out an unbelievable amount of energy right before it falls past the edge. The incredible result is what we call an active galactic nucleus. To my eyes, they are the brightest beacons in space, outshining every single star in their host galaxy combined. You and I could spend lifetimes studying them. When a supermassive giant feeds, its ring screams out in radio waves, visible light, and scorching X-rays. A few even blast out massive jets of energy, piercing through thousands of light years of deep space. As an astronomer, I look at these jets. They aren't powered by falling material, but by twisted magnetic fields amplified within that swirling disk. For us, the most extreme examples of this phenomenon are quasars. Back in the 1960s, my predecessors were totally baffled. These quasi-stellar objects looked like faint stars, yet emitted truly astonishing energy. It took time for us to realize that quasars are the blazing hearts of distant galaxies, where supermassive black holes devour matter furiously. These quasars burn so brightly, we can spot them across billions of light years. They are our cosmic lighthouses from the very early universe. Through our telescopes, we see collisions trigger this quasar phase. Left alone, an isolated galaxy often cannot channel enough heavy gas down into its very center. Spirals like our Milky Way maintain calm, ordered rotations, keeping material spread across vast disks. But when we observe two galaxies crash, that order vanishes. Gas becomes shocked, compressed, and shoved inward. Suddenly, the central black hole has an endless buffet to feast upon. You and I might expect two merging galaxies, each holding supermassive black holes, to instantly create a pair of active nuclei blazing side by side, lighting up the deep cosmic night. In some special cases, this really does happen. My colleagues and I have observed these dual active galactic nuclei, where both black holes feed heavily early in the merger. As time passes, dynamical friction slowly pulls those massive black holes together. The surrounding gas and ancient stars steal their orbital energy through slow gravitational tugs. Eventually, we watch them spiral into a tight, quiet dance. When they finally unite, they send deep ripples through spacetime known as gravitational waves. Currently, those cosmic ripples vibrate at frequencies far too low for our earthly instruments. Yet before that grand finale, the black holes enjoy a period of absolute plenty, and during this peaceful feasting phase, entire galaxies transform forever. The sheer energy these feeding black holes release goes beyond visible light. They exhale powerful cosmic winds and heavy radiation that blow deep gas away. In my field, we call this feedback. It regulates deep star formation everywhere. Sometimes that active galactic nucleus expels so much vital gas that newborn star formation completely stops. What we observe left behind is a quiet, sleepy elliptical galaxy. In other systems, those intense jets collide with dark gas clouds, compressing matter and sparking brilliant new star birth. This delicate dance between feeding black holes and galactic evolution remains my absolute favorite puzzle in modern astrophysics. It proves to us that black holes are not mere passengers, they are cosmic co-authors. Their quiet growth during these grand mergers dictates their galaxy's ultimate fate. We generally find that massive galaxies host much heavier black holes. Colossal cosmic collisions help forge this enduring, beautiful connection. As we watch distant galaxies merge, their central black holes eventually combine as well, leaving a single, monstrous giant resting deep within a newborn starry home. The exact timing of these cosmic events matters deeply, too. In the early universe, heavy collisions happened constantly. Here is something we must remember. When you and I observe distant quasars, we are actually looking backward in time, seeing them exactly as they burned billions of years ago. Back then, young galaxies were small, thick with gas, and constantly colliding. Their central black holes enjoyed endless opportunities to feast in the dark, growing to billions of solar masses very quickly. Today, the local universe is calm. Galaxies are massive, mature, and gas-poor. That is exactly why quasars are so rare now. Even so, nearby galactic collisions still paint incredibly dramatic displays for us. Look at the antenna galaxies, roughly 45 million light-years away. They are two spirals actively merging, while their black holes aren't as flamboyant as the earliest distant quasars. This rushing gas has sparked beautiful starbursts, and we believe it may still ignite stronger active nuclei. Looking closer to home, our own Milky Way and Andromeda each host a central black hole. We know they are destined to collide in about 4 billion years. When they finally merge, we suspect inflowing material will heavily feed both. They might even ignite a beautiful quasar-like phase before slowly coalescing into one single, unimaginably large black hole in the dark. To an astronomer, collisions making galaxies shine brighter is both beautifully literal and deeply metaphorical. Literally, blinding radiation from an active black hole turns a perfectly ordinary galaxy into a brilliant beacon, visible through our telescopes across vast cosmic distances. Metaphorically, they show you and me that cosmic destruction and quiet creation are truly two sides of the exact same coin. Massive collisions disrupt and dismantle, yet they also feed the black holes. They trigger gorgeous starbursts and reshape galactic forms entirely. Out of absolute chaos emerges a brilliance so intense, we watch it outshine everything else in the long night. People often ask me if black holes are simply cosmic monsters lurking in the freezing dark, waiting to blindly devour absolutely everything. To an astronomer, they are reluctant eaters. They simply stay quiet until the universe delivers a perfect feast. Galactic collisions provide exactly those circumstances. When I see that meal finally arrive in our data, the change is profound. It transforms the black hole and the whole galaxy. Through our telescopes, we see quasars and active galactic nuclei as the bright signs of this hidden feast. They remind us that the darkest cosmic objects can create incredible bursts of light. Looking deep into space, I see how these black holes can sleep for eons. But galactic collisions wake them up. I watch them feed and grow, totally changing their host's future. It proves to us astronomers that the universe uses its most destructive forces to create pure, blinding light. We don't just see galactic mergers as violent cosmic wrecks. They give black holes a chance to shine brightly in our sky surveys. They turn the pitch-black cosmos into a massive stage, lit up by their endless hunger. Sit with me at the observatory for a moment. You might picture galaxies as lonely islands floating in a dark ocean, but my star maps show a reality that is far more deeply connected. Through my lens, galaxies aren't lone wanderers, they have families. They huddle in groups, clusters, and massive superclusters stretching across distances I can hardly measure. When I observe a collision, I'm not seeing a solo event. It is just a small act in a grander play. We call this massive structure the cosmic web, and in my line of work, that web is not just some poetic idea. It is a very real structure that we have mapped out through our largest and most ambitious sky surveys. When I plot the coordinates of thousands of galaxies, it becomes clear they aren't just thrown into the dark at random. I see long filaments of galaxies and dark matter snaking through the void, crossing each other at incredibly dense knots to form giant clusters. Between these bright strands lie massive voids. Looking into those regions, galaxies are rare and space feels hauntingly, beautifully empty. From my desk, the whole universe looks like a giant, three-dimensional spiderweb, glowing softly with starlight instead of morning dew. Our own Milky Way belongs to the local group, a modest little neighborhood of about 50 galaxies held tightly together by gravity. Looking closely, I can spot familiar neighbors. Andromeda, the smaller Magellanic Clouds, and dozens of dwarf galaxies orbiting quietly out of sight in the deep shadows. But my charts show our group is just one tiny thread in the Virgo supercluster, and that is just a slice of Laniakea, a massive cosmic continent spanning over 500 million light-years. Whenever galaxies crash in our little corner, they are simply ripples in a much larger interconnected sea. Look at this with me. In this context, these collisions aren't accidents, they are completely inevitable. When I point my telescope at crowded cosmic neighborhoods, I see galaxies forced to interact. Hundreds, sometimes thousands, share the exact same tight space. Close calls happen constantly. I measure how the huge gravity of the whole cluster herds its members into an incredibly dense pocket. Here I watch these star systems constantly get tugged, twisted, or totally stripped of their gas. Some pass by gently, while others violently merge, completely reshaping the galaxies I observe. I find these clusters absolutely fascinating. Through my X-ray monitors, they aren't just piles of galaxies. They are giant pools of hot plasma that hold far more mass than every single star inside them combined. When I see galaxies colliding in here, that glowing plasma adds serious drama. I watch it slow them down, boil away their gas, and completely change their evolution. I love studying the famous bullet cluster. It shows two massive clusters slamming together spectacularly. The galaxies inside usually glide past safely, but my scans show their hot gas crashing together, carving out a massive shock wave shaped exactly like a bullet. Zooming out on my screens, superclusters are barely bound together. They look like giant archipelagos to me, just islands of star groups tied by thin glowing filaments spanning hundreds of millions of light years. I track collisions here too, though they take eons to unfold. It reminds you and me that no galaxy is ever truly alone. When I find the loneliest galaxy in the night sky, my models prove it is still anchored to a hidden filament, woven deeply into the cosmic web. The most amazing part of my job is seeing how this web matches the exact processes that fired up right after the Big Bang. I look for tiny density differences. Those incredibly small bumps in an otherwise smooth sea of matter and energy eventually grew heavy, pulled by raw gravity. The pockets holding slightly more mass pulled in extra material, forming thick filaments and clusters, while emptier spots just became dark voids. After billions of years, that lumpy start evolved into the massive, glowing network my telescope captures tonight. I realize these violent galactic mergers are just a natural part of that ancient growth. The cosmic web is simply rebuilding itself, funneling star stuff down its long, shining threads. I find deep peace realizing that what seems chaotic to us, the crashing star systems, the violent birth of new suns, even feeding black holes, they all belong to a grand pattern unfolding for billions of years. As an astronomer, I see every act of violence balanced by the quiet cosmic web. It is a deep space structure so vast, the largest galaxies look like simple dust. These galactic collisions are not accidents, they are the very threads weaving everything tightly together. Looking at the data, it humbles me to see our own existence tied to this vast structure. Past mergers completely shaped our Milky Way. We actually carry the silent remains of smaller, absorbed star systems. Their ancient stars drift in our halo. Elements forged in those dying stars scattered across the void. Eventually, that exact material formed our sun, our Earth, and you and me. Even we astronomers, staring up in quiet wonder, are simply products of this giant cosmic web. This invisible web pushes me to think beyond mere physics. Just as galaxies anchor to heavy filaments, our own brief moments of life bind together in hidden patterns. A galaxy looks like a lonely island until my maps reveal its hidden ties. Just as you might feel alone until you step back and see the wider network of history you belong to. Whether between drifting galaxies or human ideas, collisions matter. They create sudden points of contact, sparking intense growth, deep change, and entirely new beauty. Out in the deep cosmic web, true isolation does not exist, only varying connections. Star clusters pull on each other across millions of light years, answering gravity's gentle call. Galaxy clusters bloom where dark matter filaments cross, tying the net together. Inside these knots, galaxies merge and settle into fresh shapes, yet the larger design remains. This dark web is fragile yet eternal, looking like delicate lace, yet holding strong across billions of years. When you and I zoom out to view the entire observable universe, the calm is profound. Collisions shed their violent nature when viewed within this massive, slow dance. Just like ocean waves are never a mistake, but the voice of the sea itself. Through my lens, galaxies do not just blindly smash together. They ride along the dark filaments, steered by the exact structure that first formed them. Ultimately, the wider universe teaches us a simple lesson about being completely connected. These distant realms might burn bright, fade out, or crash beautifully, but none exist completely alone. They are just chapters in a massive text written by the cosmos itself. A record where every galaxy is both reader and writer. Every single collision forms a paragraph in a story spanning billions of years. The web promises that nothing is ever lost. Every cosmic meeting drives the universe slowly forward. As a scientist, I find this vision incredibly soothing. It is a giant woven framework where even the most violent crashes sing as part of a deeper harmony. Galaxies strung like glowing pearls on dark matter threads remind me that pure connection anchors all existence. And when we finally look up at the dark, those stars are never scattered by chance. They are bright markers of a web pulling us all into one story. But out in the dark, galaxies are not just dancing gracefully. They are also highly opportunistic and hungry eaters. Massive future mergers between the Milky Way and Andromeda often grab the popular science headlines. But a quieter truth plays out in my telescope: galactic cannibalism. This happens when a massive galaxy slowly eats a smaller neighbor, ripping the victim apart star by star until nothing remains but thin ghosts of stellar dust. It is basically interstellar snacking on a giant scale. The universe overflows with tiny dwarf galaxies, dim little groups of stars and dark matter, thousands of times smaller than the massive spirals we normally study. They circle the big galaxies like bees around a hive, held by gravity but incredibly fragile. To a heavy spiral like our Milky Way, a passing dwarf galaxy is less a threat, more a light meal. Gravity simply pulls and tears until the little companion completely vanishes into the main galactic disk. I see this constantly. It has shaped nearly every massive galaxy out there. In fact, our own Milky Way is an absolute apex predator. If you and I examine its faint outer halo right now, we will spot ghost trails of stars completely foreign to our spiral arms. These tidal streams are the chewed-up remains of galaxies we already swallowed. They serve as silent proof that our home grew not just through quiet star birth, but a brutal history of eating our galactic neighbors. Tonight, you and I are watching a cosmic meal unfold, the slow destruction of the Sagittarius dwarf galaxy. We discovered it in the 90s. I watch as our Milky Way's gravity pulls this tiny neighbor apart. Long ago, the Sagittarius dwarf orbited us like a loyal friend. But I track how its orbit decayed over time. Now it stretches into a massive ribbon of stars, wrapping around our galaxy like a frayed, glowing scarf. Every time it plunges through our galactic disk, we see more material torn away, leaving beautiful glittering streams arcing through the darkness. I know Sagittarius will eventually be swallowed whole. Its stars will blend right into the Milky Way's family, pretending they were born here all along. But peering through my telescope, I don't see violent crashes or massive stellar explosions. For the actual stars inside that dwarf galaxy, the whole thing feels completely calm. They are so tiny compared to the deep void around them, they almost never touch. Instead, I track these stars drifting into new paths, gently carried by a silent gravitational tide until they fade, spread incredibly thin across the cosmic dark. If you were standing on a planet orbiting one of those stars, your night sky would slowly warp over billions of years. Familiar constellations would drift and break as your home galaxy dissolves, but through my lenses, I see Sagittarius isn't dying alone. Our Milky Way hoards a few smaller satellite neighbors, like the Magellanic clouds out in the deep southern sky. I spend nights watching these two messy galaxies locked in a slow, gravitational waltz with us. The large Magellanic cloud looks pretty sturdy for now, but my computer simulations point to a darker future. It might eventually get dragged entirely into the Milky Way, slowly merging into our own star count. For now, it just bleeds a trail of gas called the Magellanic Stream, pulled outward by our heavy gravity. Let's step back, though. This kind of galactic cannibalism has shaped the universe since the beginning. When I study giant ellipticals, those massive, smooth star fields resting in the centers of clusters, the data proves they grew by gorging on countless smaller victims. I spot their halos littered with faint star streams, the fingerprints of a greedy past. We astronomers call these giants the heavyweight champions of deep space dining. They got that big through billions of years spent slowly digesting their neighbors. I see a vivid example every time I image Andromeda, our nearest massive neighbor. My scans of its outer edges reveal a messy patchwork of star streams, leftovers from old cosmic meals. Actually, I can tell Andromeda devoured several big dwarf galaxies over the eons. It hides a deeply violent history of cannibalism and endless slow mergers. When Andromeda finally crashes into our Milky Way, it brings that giant appetite right to our doorstep. And together, our two homes will share a long record of swallowed companions. Why does the universe eat itself like this? For me, the math always comes down to gravity. I measure massive halos of dark matter wrapped around large galaxies. It's totally invisible, but it reaches far beyond the stars, creating a trap of pure gravity. When tiny galaxies drift too close, they get permanently trapped. I watch their orbits drag, bleeding energy into the endless friction of gravity. Over billions of years, they quietly spiral inward, snapping apart until they vanish into the hole. For those of us looking through the telescopes, this isn't just morbid curiosity, it's our best clue. By tracing these ghostly tidal streams of dead stars, I can piece together the deep history of our galaxy. It feels like cosmic archaeology, only instead of digging up broken clay pots, I'm finding whole lost populations of stars painting huge arcs across the night. These glowing fossils let me map out the completely invisible dark matter, pulling the strings behind everything. It gives me a peek into the universe's hidden skeleton. Despite the terrifying name, galactic cannibalism really isn't about destruction. It's how galaxies breathe, grow, and change over time. The Milky Way I study every single night would look completely different without its constant diet of smaller dwarf systems. The stars we steal from them pack our outer halo, mixing fresh chemicals into our home and throwing beautiful variety into the deep edges. Even our own sun might owe its heat to the leftovers of past galactic snacks. Since the heavy elements in your blood often come from stars born in tiny galaxies that we ate long ago. You and I have to admit there's a certain deep elegance here. There are no roaring fires in space, no jaws snapping shut, just endless, quiet patience. Over hundreds of millions of years, gravity gently unpicks a small galaxy, stretching it into a soft glow that slowly fades into the larger whole. Through my telescope, it looks more like watching morning mist drift apart in the wind than a cosmic slaughter. Through my telescope, I see how the universe proves even destruction holds its own beauty. Leaving behind rivers of stars tracing graceful arcs in the dark, honestly, humor has its place at this cosmic dining table, too. To astronomers like me, if space were a restaurant, dwarf galaxies are appetizers. While massive collisions like the Milky Way and Andromeda act as the main courses. Right now, I track the Sagittarius dwarf getting nibbled away, a quick snack for our galaxy lasting billions of years. And when Andromeda finally arrives, it becomes a feast to end all feasts, completely reshaping both galaxies into something entirely new. Galaxies, I've realized, are not just dancers. They are gourmets forever dining on each other in the quiet dark, and my data shows this habit creates transformation, not just waste. Those tiny galaxies vanish, yet their stars live on. Woven into the fabric of larger star systems, from my observatory, this cannibalism feels less like loss and more like rebirth, where each disappearing galaxy fuels the sheer grandeur of the survivors. It is a cycle we have traced back to the earliest epochs, and it will keep running as long as these galaxies exist. When I view it this way, galactic cannibalism becomes less a story of pure destruction and a gentle reminder of interconnected cosmic life. The scattered stars of a devoured dwarf do not simply vanish. They join the vast chorus of light in the larger galaxy, shining just as bright, simply placed in a brand new arrangement. Ultimately, what looks like a quick cosmic snack to us is a quiet act of creation, the universe folding small stories into a grander narrative. I've learned that deep space is incredibly restless, never content to just let galaxies sit quietly in their dark corners of the cosmos. Gravity, the great cosmic matchmaker, makes sure galaxies drift toward each other, slowly entwining in dances lasting billions of years. Right now, I track these mergers as scattered, dramatic events, little highlights for specific star systems. But let's stretch the clock forward together. In the deep future, galactic collisions become more than isolated spectacles. They become the main story of the universe itself. Our own Milky Way is fated for this exact future. I'm charting its collision with Andromeda, which creates a massive hybrid system my colleagues jokingly call Milkdromeda. That crash won't be the end of our story, though. Far from it, once Milkdromeda settles into its smooth elliptical shape, my models show it will keep pulling in smaller galaxies nearby. The Triangulum Galaxy, the third biggest member of our cosmic neighborhood, might get swept in. Ensuring our local group eventually forms one massive elliptical galaxy wrapped in faint debris streams. What I map today as galaxies scattered across millions of light-years condenses into one luminous heavyweight. And this process is not unique to us. Looking across the cosmos, I see galaxy clusters heading toward the exact same fate. Smaller galaxies get slowly consumed by larger ones, while clusters themselves tighten as members interact and merge. On cosmic scales, these collisions aren't just chaos, they are pure consolidation. Galaxies gather together, forming fewer, much larger systems. It feels like a slow convergence, just gravity patiently gathering its cosmic flock. The physics here are simple. Dark matter halos, those invisible cocoons of gravity wrapping our galaxies, stretch across immense distances. When these halos overlap, galaxies become permanently bound together, slowly spiraling inward over billions of years. Left unchecked, my calculations show a future universe dominated by enormous elliptical galaxies. Each one built from countless cosmic meals. The universe won't always look like the beautiful, spiral-rich cosmos I photographed today. Instead, its distant future will be a silent sky of smooth, rounded giants glowing quietly without those delicate spiral arms. As space ages, these galaxy mergers become rare but vastly more impactful. Right now, my lens shows galaxies resting fairly close together, making deep space collisions common over the eons, but cosmic expansion complicates everything. Space itself keeps stretching, pushed by dark energy, and I watch distant galaxies get carried farther and farther into the dark. Over vast time scales, only the galaxies bound by gravity, like our local group, will remain accessible to us. Everything else eventually slips past the cosmic horizon, receding faster than light due to that rapid expansion. Because of this, Milkdromeda and its future mergers represent a rare, beautiful last act. Beyond our tiny neighborhood, the rest of the universe's galaxies are destined to just disappear from our view completely. You and I can only imagine a civilization trillions of years from now, long after the Milky Way and Andromeda become one. Looking through their telescopes, the universe will seem so much emptier than ours today. Future astronomers will look up and find only their own giant galaxy filling the night sky. The countless deep sky objects I photographed tonight, spirals, dwarfs, irregulars, will be completely gone from view. Their cosmos will look strangely empty, as if their home galaxy was the only one ever created. You and I know those galaxies aren't gone, it's just that cosmic expansion will pull them into unreachable darkness. As an astrophysicist, I find galactic mergers visually stunning, yet deeply sad. When our Milky Way finally hits Andromeda, it will be a breathtaking grand finale, a literal fireworks display made of starlight. But it also drops the curtain on our wider cosmic stage. Every bound local group will be stranded in an increasingly dark, empty void. This violent era of crashing star systems will slowly fade into an age of total cosmic isolation. Inside these lonely future galaxies, individual stars will just keep repeating their cycles of birth and death. For a long time, these mergers will trigger massive starbursts as giant molecular clouds slam together and compress. Quasars will ignite, making these systems brighter than we've ever observed, but stellar gas is a strictly limited resource. Once black holes expel that gas or new suns eat it up, the fuel tanks run dry. Star formation will grind to a permanent halt. Those massive elliptical galaxies we see forming after collisions will age into quiet graveyards of long-lived stars. Over trillions of years, the faint glow of these galaxies will keep dimming. The supermassive stars will be long dead, they'll leave behind only tiny red dwarfs which quietly burn for eras. Those dying ember stars will cast a soft red glow, nothing like the vibrant blue spirals I study today. Even when galaxies do crash in that distant era, we wouldn't see any bright flashes. There's just no gas left to spark new suns. Instead, those late-stage mergers will just shuffle around dying stars, folding one silent system into another. And then, in a future so deep it hurts my head to calculate, even those red dwarfs die. Our majestic galaxies will become ghost towns of stellar corpses, white dwarfs, neutron stars, and black holes drifting in total darkness. Impacts might still happen, but they'll be completely dark events, smashing dead remnants together instead of sparking new light. Eventually, physics tells us even black holes will evaporate through Hawking radiation. They'll leave behind nothing but faint thermal whispers in a freezing, empty void. In this cosmic timeline, galactic collisions aren't just an old chapter in our textbook. They are the actual road paving the universe toward its final fate. They construct the massive supergalaxies of tomorrow, even while setting the clock for the slow death of starlight. Every cosmic impact is beautifully destructive, a brief, blinding flash that pushes the cosmos one step closer to eternal silence. Think about that with me for a second. It's sobering, but honestly quite calming. The universe isn't rushing towards some sudden catastrophe. Instead, our universe is gently dimming, one merger, one fading star, one galaxy at a time. Billions of years into that dark era, these massive gravitational mergers will be the final grand performance before total silence falls. Even then, the data left by these collisions will survive in the weird shapes of the galaxies they warped, the stars they ignited, and the supermassive black holes they fed. Looking through my telescope tonight, these collisions look like violently chaotic spectacles. Star systems smashing together, nebulas igniting, giant black holes roaring. But from the standpoint of cosmic time, they are just the slow evolution of our universe from chaotic youth to a silent old age. I've learned galaxies aren't just cosmic dancers, they are massive, slow-moving builders. Their deep space impacts physically shape the architecture of the cosmos for as long as time exists, so the story definitely doesn't end with Andromeda. It spans across billions and trillions of years, echoing into a distant era where deep space goes dark, but never loses its meaning. Even when the light completely fades, those quiet, fused galaxies will just drift through the expanding vacuum. They'll carry the physical history of every violent impact that forged them. So you see, these mergers aren't just a modern telescope spectacle. They are a physical bridge to the deepest future, tying together our cosmic past, the present, and the final whispers of reality. I study these galactic collisions because they aren't just random accidents. They are the essential structural engineers of the entire night sky. The beautiful cosmos I photograph every night simply wouldn't exist without these massive gravitational crashes. The spiral arms, the starbursts, and the vast galaxy clusters strung like pearls along dark matter filaments, they all owe their lives to these collisions. When we watch two galaxies merge through our lenses, we are witnessing cosmic evolution live, building perfect structure out of pure, cosmic chaos. Tonight, you and I are looking deep into space. Long before two galaxies meet, their hidden dark matter halos pull at one another. That massive gravitational handshake kicks off everything. In my observations, I watch these galaxies stretch out, throwing long tidal tails of starlight and dust across the void, outlining gravity's quiet pull. These cosmic events trigger massive starbursts, igniting fresh generations of suns that would otherwise stay dark. Without these mergers, our universe would lack so many stars, exoplanets, and maybe even life. For us astronomers, these collisions solve some of the deepest mysteries out there. By tracking them, my colleagues and I learn how delicate spiral galaxies warp into smooth ellipticals. We discover why some cores blaze with bright quasars while others go quiet, and how dark matter bends the light. Every galaxy merger is a giant physics experiment. It plays out on a scale so huge that only ancient starlight reveals the final result. But beyond the hard science, these impacts show me how the cosmos creates art out of total violence. The images we pull from space telescopes show galaxies embracing, their spiral arms twisting into glowing arcs, feeding supermassive black holes at the center. Looking at the data, it feels less like destruction and more like creation. Massive paintings drawn by gravity and deep space light across the dark. Every single crash is a unique masterpiece, yet tied to the same physics. Sitting at the observatory, I always reflect on what this means for cosmic change. These crashes look deadly, but they actually build more than they break. Individual stars almost never hit each other. The space between them is just too vast, keeping them perfectly safe. Instead of total ruin, mergers actually bring renewal. We see sudden bursts of starlight as galaxies reshape themselves, giving black holes fresh gas to consume. Even the messy parts follow a strict cosmic order, binding star systems into massive structures over billions of years. Watching this teaches me a real lesson in endurance. A whole galaxy can be shredded, stretched out, or completely remade, but it survives. Those stars just keep drifting around whatever new center gravity builds for them. The gas clouds settle down, clumping back together into glowing stellar nurseries. Out of the crash comes survival. The night sky proves that dramatic change isn't the end of the line. It is just the slow, steady rhythm of the physical universe. As a scientist, what strikes me most is the extreme patience involved. These gravitational dances drag on for hundreds of millions, sometimes billions of years. What seems like a brutal impact is really just a slow unfolding, playing out like a quiet symphony across deep cosmic time. Stick with me here, we only ever capture brief snapshots, a dust tail here, a bright starburst there. But on a cosmic scale, it is one graceful motion, two massive star systems weaving together in total silence. That massive scale makes these events deeply comforting. They show me that things looking completely catastrophic up close are, over billions of years, just playing their part in a much larger cosmic harmony. These galaxies survive the change, and the universe does too. Instead of random chaos, my research shows how beautiful order naturally emerges from disruption. It is genuinely humbling to realize our own home galaxy will face this. The Milky Way, holding billions of stars and countless little planets, is already falling toward the Andromeda galaxy. Knowing this future is coming doesn't scare astronomers, it just proves we live in a universe built on deep cycles. Our Milky Way is not ending. It will simply fold into something bigger, writing a new chapter beyond its current spiral shape. Just like single stars are born and die, whole galaxies go through phases too. These giant mergers are simply their way of transforming. Tracking these events really proves how connected the cosmos is. No galaxy floats completely alone. They are all tied together by gravity, forming massive cosmic webs of clusters and shining superclusters. These crashes act like giant threads pulling the web tighter, making sure no corner of deep space evolves by itself. So when I point my telescope at galaxies billions of light years away, I am not looking at something strange. I am watching the exact same forces shaping our own cosmic neighborhood. The real magic of these galaxy crashes isn't just the glowing cores or bright light, it is what they teach us about sheer resilience. They prove that heavy cosmic change always carries the hidden seeds of creation. They show me that for all its raw power, the universe works like a slow gardener, pruning, shaping, and feeding new stars. Even when massive spiral structures break down, their matter lives on in new ways. And honestly, on a human timescale, they move way too slowly to fear. Let's think about this together. They prove that cosmic endings are rarely final, that huge upheavals are really just quiet preludes to new starry patterns, and that surviving simply means accepting change. Through my lens, I see galaxies teach this silently. They drift into collisions with a grace only visible across deep cosmic eons. For me, these galactic mergers truly matter. It is simply how our universe sculpts itself. I watch them shape star systems, ignite fresh stellar nurseries, and expose the unseen pull of dark matter. They matter because they are simply beautiful, pure, raw, natural art painted in starlight. And they reflect truths far beyond my daily equations, showing that change is beautifully constant. That cosmic cycles never stop. Real endurance comes from changing form rather than resisting it. When you and I look up to study these collisions, we glimpse the sheer scale of space and its quiet wisdom. Tracing their glowing arcs on my screens, I hear them whisper, deep inside cosmic upheaval lies beauty. every ending sparks a brand new beginning. It is a sprawling story of deep space renewal, written across billions of quiet years. A comforting reminder that our universe thrives entirely because of change. I watch these vast galaxies collide, but not at all in the violent way most people picture. I hear no deafening crashes and see no sudden explosions, just the slow, incredibly patient choreography of gravity. These massive encounters span hundreds of millions, sometimes billions of years. They move so gently that if I could watch them in real time, the sky would look as still and calm as the turning of seasons. What looks like pure violence from down here is actually a graceful inevitability, a gentle cosmic reshaping rather than ruin. I know our Milky Way is heading straight for the Andromeda galaxy, but you and I truly have zero reason to worry about this. The deep time scales I measure are almost impossible to grasp. It will not hit tomorrow, not in 1,000 years, nor a million. Billions of years separate us from that distant stellar meeting. That is far longer than our own sun will even manage to keep its current shape. So please do not cancel your weekend stargazing plans, or lose any sleep over it. Long before those spiral arms finally touch, humanity's place in the wider cosmos will have completely shifted anyway. I focus entirely on what these mergers teach us. Looking at sweeping rivers of starlight, my instruments prove the universe is not random chaos, but beautifully ordered. Even in galactic upheaval, I see balance. Even in dark endings, there are beginnings. Galaxies will twist, stretch, and bleed into each other, yet they endure, forging new shapes, new planetary homes, and fresh patterns etched deep into the sky. I find that fact strangely comforting. If entire star systems survive the violent gravity of these massive encounters, then maybe pure endurance is woven directly into the fabric of space itself. Cosmic change, no matter how massive, is never destruction, just profound transformation. In the freezing silence of space, watching starry islands slowly drift, the universe constantly reminds me that deep time softens all turbulence. So, as you and I pack up the telescope tonight, rest easy knowing the cosmos moves with extreme patience. What looks like chaos out there is really just creation working. And across billions of long years, stellar beauty endures quietly, gracefully, and completely unshaken by the slow dance of gravity.